another round of exciting talks and discussions. Thank you for joining us again. And let's begin with our first speaker, Dr. Irene Tubikanek.
That's fine.
Dr. Irene Tubikanek is a postdoctoral researcher at the Institute of Applied Statistics at Johannes Kepler University, Linz in Austria, with expertise in stochastic models and their numerical and statistical applications. Today, she will present her talk on network inference in a stochastic multipopulation neural mass model via approximate Bayesian computation. Before we proceed, Dr. Tubikanek, could you share with us what motivates you to dedicate your energy and time to mathematical activity every day?
Yes, of course. So first of all, let me thank you again for the invitation and for the possibility to share my research at this very nice conference, which gives women working in math a platform to interact. So I think events like this are very important. Good, so what is my everyday motivation? I would say there are many aspects that I like about my work, which in fact is very diverse. So I also like a lot teaching math, I have to say, so especially when I can talk about advanced topics which are also related to my own research. Like this semester, I teach a course in stochastic processes, which is also my own research area, and I really like to give students a taste of possible research topics also when I'm doing lectures. But what I really like or what motivates me when I do math, so let's say when I teach or also when I participate in committee work, then I have to be very present, like very much in the here and now. And when I do math, it in a way brings me into another world, like in the sense that I'm then very, very focused on my problem, on the proofs, without noticing much around me. And this is something I really enjoy with doing math. And maybe if I can use this to also give you maybe some advice from my own experience, then well, never think that you are not good enough for doing math, for doing research, for surviving in academia, because it's completely normal that everyone has some self-doubts from time to time. And I mention this because it's well known that especially among women, this happens a bit more often. So my advice is trust yourself. And if you have some issues, then talk to someone whom you trust, because I mean, I would not be where I am now without the support from many people in the background. Good.
Nice. Thank you very much for sharing this, Professor.
Of course. So I guess I will now share my screen.
Yes, thank you.
Okay, so you should see it.
Yes, we can see.
Okay, then maybe, I mean, you introduced me already, but let me also say a few words about myself. So my name is Irene Tubikanek, and I'm currently a postdoc on a tenure-track position at the Johannes Kepler University in Linz in Austria. So probably you know Austria. Oh, sorry, I cannot. Ah, yeah, now it works. Probably you know Austria, right? This small country in Central Europe, not to confuse with Australia, which in fact is very far away. And well, my university is located in the northern part of Austria. Here you see the campus of the university. It's a rather big one, at least in Austria, we believe it is a big one. So there are many buildings. There is a large pond. Can you see my mouse when I move it? Okay. Yes. There are some high towers, and my office is located on the northern right part. So it is in this building over there. And maybe just to give you a taste, So this is another picture of the campus of my university, and my office is in this building number 14. So while sitting in this building, I developed one of my research topics that I now like to share with you. Good, so and I want to motivate my research or the topic that I present today with this picture. So what you see here is a multi-channel EEG dataset, which has been recorded during an epileptic seizure of a patient. So probably you know that EEG is what can be measured by putting electrodes on the scalp. Each electrode measures the activity of one population of neurons, one region in the brain, and yields one such signal. And these 4 blue signals here on the slide were recorded with these 4 yellow electrodes. So there were 2 on the left brain hemisphere and 2 on the right. And the goal of this talk will be to understand if and how these, in this case, 4 brain regions interact with each other. So we are interested in directed connections among these, in this case, 4 brain regions, and we want to estimate them based on observed data of this type. So based on such multi-channel EEG recordings, which corresponds to multivariate time series data. Good, and how do we want to do that? So we will talk about 3 parts. In the first part, we will develop a stochastic model which is able to reproduce such multi-channel EEG data. And this model will be a stochastic differential equation, and it will contain these network values that we are interested in as model parameters. So we will have parameters that are either 0 or 1. They are 1 if there is a connection from one neural population to another, or 0 if there is no connection. And let me jump to the third part of the talk. So in the third part, we will develop a simulation-based parameter estimation method, which we want to use to estimate these network parameters, these 0-1 coupling connection parameters. And this simulation-based method, it will be based on what is called approximate Bayesian computation method. And this approximate Bayesian computation method will rely on a huge amount of data sets that we simulate from our model. And this brings us to the second part that we first have to treat, because we need a reliable method, a reliable numerical method to simulate from our model. Okay, and in the second part, we will derive such a method, and it will be based on the so-called numerical splitting approach. Good, so let us do one thing after the other. We start with the first part, where we will introduce this multi-population stochastic neural mass model. Good, and so the model that we will use, so it's not that I introduced the model, we use something which has been developed in the 90s, a model that dates back to the work of Janssen and Ritt. And the model has also been reformulated and analyzed later by colleagues of mine from the JKU in Leeds. So how does the model look? We start with modeling one single neural population, which can be measured with one EEG electrode. And to model one neural population, we need a 6-dimensional equation. The reason for that is that each neural population is modeled as a system of 3 interacting groups of subneurons. We have the main cells, and then we have excitatory and inhibitory interneurons, for each of which we need a 2-dimensional system to account for their oscillatory activity. Good, and this gives us this 6-dimensional equation, and what can be observed or measured with an EEG electrode is only the difference of 2 of the model components. So none of the components are directly observed. We only observe the difference, which describes the input that the main neurons receive from the excitatory and inhibitory interneurons. So this is what can be measured with EEG recording techniques. What else do we see? We see that the model is nonlinear. It contains the sigmoid function, which is, however, globally Lipschitz and bounded. So everything behaves nicely from a mathematical point of view. The model contains several parameters which are all biologically motivated. Important is, for example, this capital A parameter here, because it describes the, let's say, amount of excitation, the amount of activity in this neural population. And well, the equation is driven by standard Wiener processes or Brownian motions to model the stochasticity in the brain. Good. So to summarize, we need a six-dimensional equation to describe one single neural population whose activity can be measured with one EEG electrode. And the question is now, how can we model n possibly interacting neural populations? So we may take this SDE from before and say that the cave population can be described by exactly that system. We just assign an index k to all of the model components. Good, then in addition, it might be plausible to assume that each neural population has its own behavior. So we may assign an index k also to all of the model parameters. Good, and then we have now a model for n neural populations, but they are not yet coupled. So what we still have to do is to find a proper coupling of these populations. And here we follow a strategy which has been proposed by Wendling and co-authors in the year 2000, which is to introduce a coupling term such as the red term here, which tells us that the cave population receives input from the main cells, the X1s, from all other populations. And from a modeling point of view, this input is excitatory, which is why we place it on the fifth dimension of the population that we are currently looking at, because the fifth dimension corresponds to the derivative of the main cells of that population. And what is important in this term are these raw JK parameters, which can be either 0 or 1. So these are exactly those parameters which define the network among these n populations. So they are 1 if there is a connection from population J to K, or 0 if there is no connection from J to K. And these capital K parameters are coupling strength parameters, so they can assume any positive real value. Good, and now I'd like to show you a bit the impact this coupling term has on the model. So we look at an example for n equal to 4 neural populations. In this example, none of the populations are coupled, and also they all show a not very interesting, let's say a non-active activity. Now we can activate the first population by increasing this capital A parameter. So if you remember, I told you this A parameter describes the amount of activity that we have in this population. So I increased it. But still the populations are not yet coupled. So all these raw parameters are set to 0. And now we want to see what happens if we introduce a coupling in the way that the first population influences the second the third, and the third, the fourth. And if we do that, we see that through this coupling, we achieve an activation also of other populations. And in this case, we used, let's say, a moderate value for the coupling strength. if we increase the strength of this coupling, then we see that all populations are activated one after another, and we observe a so-called synchronized brain activity. Good, so this was to give you an idea of the model and its behavior. And now we come to the second part, where we have to find a numerical method which allows us to simulate from this model, because the model is too complicated to find an explicit solution, so we have to treat it numerically. Good, and here we will work with a so-called splitting method, and in particular we extend a method that has been introduced already for one single neural population, and now we want to extend it to the case of this n-coupled population, so this much bigger stochastic model. And the main idea for this method, so it is based on first rewriting this big SDE in a much more compact way from which it is easier to derive a numerical method. And in particular, we will write it as a so-called damped Hamiltonian system, for those of you that are familiar with that. Good, so let us see how we can rewrite this rather very complicated big SDE in a much simpler form. Good, so maybe you noticed that, I don't know if you can notice it, so I will tell you that we could combine, for example, these three components that I colored in orange together in a three-dimensional vector that we call QK. You see it here in the bottom. We could do the same for the other three components, X4, X5, and X6 of the cave population, and combine it in a three-dimensional vector PK. Then you may see that here on the right side, this PK appears again. So I write it also here in the bottom. Now we could combine these three terms, which I marked in blue. We see these terms only depend on X1, X2, and X3, so only on the QK component of the system. So we could write it like this here, and we combine the parameters A and B into a diagonal matrix that I call gamma. In a similar way, we can treat these three terms that I colored here in red. So they only depend on X4, X5, and X6. So only on the P component of the system, which is why we could write them like this here, again with this diagonal matrix that contains A, and B in the diagonal. Good, we could also combine what I color here in gray, so the nonlinear terms with the sigmoid function, as well as the coupling term, into a function that I call GK. And we can see that this function, again, only depends on the Q component of the system. So we have X1, X2, and X3 from the cave population, and then also the X1s from all the other populations, but it's only this Q component. Good, and similar for the three Wiener processes, we could combine them in a three-dimensional vector of Wiener processes, and we have some noise parameters here that we combine into a diagonal matrix sigma k. Good, so it was just a kind of clever rewriting of this big system to obtain something more compact. Good, and this is what we obtain for the cave population, but in order to be able to derive a numerical method for this system, we really need a formulation for the whole big 6n dimensional SDE. But this is now straightforward. So we proceed completely analogously. We just combine all the n three-dimensional QK vectors into a bigger one that we call Q. We do the same for the P component, for the Wiener processes, and for the nonlinear functions. And then for this gamma and sigma matrix, which contains model parameters, we use larger diagonal matrices, which contain all the corresponding parameter collections from all the n neural populations. Good, so what I wanted to say is we can rewrite this very big, actually arbitrarily large 6n-dimensional STE into a very nice compact form like this. And now here we have this classical formulation of an STE, where here we have the drift term, here the diffusion term, which is constant in our case, and then the whole thing is driven by some suitable Wiener process. Good, so having this expression, what is now a suitable numerical method that we could use here? So probably for those of you who are familiar with this type of equations, or maybe with ODEs at least, you may say, well, why not using a standard Euler or Euler-Maruyama approximation for this equation? Euler-Maruyama, it works like this. So I should say when we do numerics, we introduce a discretized time interval because we can only do simulations on discrete points in time. And then we want to know how can we get to a value at time ti plus 1 from the previous one at time ti. And delta I call the distance between two times on discrete, right? And it's equidistant. We always have the same delta between two consecutive points in time. And the Euler-Maruyama method just takes the previous point, it adds the drift f evaluated at this point times length of the current time interval. Then we add the diffusion, it's just constant in our case, and this should notate an increment of the Wiener process. Good, and well, this method is convergent because our STE is globally Lipschitz. So yes, in terms of convergence, it performs very nicely. But the problem with this standard method is that in some situations, it is not very good in preserving the structure of the equation. So for example, it does not preserve well oscillations, and here we have oscillations because brain activity is oscillatory. And in particular, what it does is that it totally overshoots the amplitude of the oscillations. So it would yield realizations from the model with way too large amplitudes, unless we choose an extremely small time discretization step delta. But when we choose delta very, very small, then the method becomes extremely inefficient because then we have to evaluate a lot of points, which we don't want to because later we want to use the method within a simulation-based inference method. So this is just too computationally heavy. And this is why I like to work with so-called splitting methods. In terms of convergence, they are comparable with the standard method, but they have shown to be much better in preserving oscillatory dynamics, for example. So it allows me to use larger deltas while still obtaining the correct dynamics from the system. Good, so I'd like to show you how such a splitting method works. The main idea behind this method is, well, to take your STE, which you cannot solve exactly, and to try to divide it into several subsystems. In this case, we will need two, and which are both simpler so that they can be solved exactly. Then you treat the systems separately, you solve them, and then in the end, you combine again your solutions to obtain a numerical method for your original equation. So let us see how this works for this model. The reason why this STE cannot be solved exactly is this non-linear term G here. which contains the sigmoid function and also this big coupling term. So the idea is to exclude this and to look at these two equations where we treat the nonlinear term separately. So we have a linear SDE. So because everything here that I colored in green just forms a linear SDE even with additive noise. Only the red term is nonlinear, which we exclude and we treat via a separate deterministic system. So the second one is an ordinary differential equation. And the nice thing is that both of these equations we can now solve exactly. So let us start with the first one. So this system can again be slightly rewritten into this classical form of a linear SDE, where we have a matrix A bar in the drift, which has a very nice block structure. So this block structure comes from how we reformulated the model. And we just have additive noise. And we know how to solve such a linear SDE. So the solution contains the exponential matrix of this matrix A bar that we had here in the drift. And it contains a normally distributed component with a zero mean vector and a covariance matrix where also this matrix exponential enters, as well as the noise matrix sigma. Good, so we can nicely write down the solution. But to be really able to implement the method, we need closed form expressions for these two matrices, for the matrix exponential and for the covariance matrix. And they are often not easy to obtain, especially in such high dimensional setups. But in our case, since we have such a nice block structure of the matrix A bar, we can obtain quite compact closed form expressions for these two matrices. I just show them to you here so that you can get an idea that it's not too heavy. We can write down these two matrices. Good, so we solved the first equation exactly, and we want to do the same for the second one, the deterministic one, which is nonlinear. But the nice thing is, if you look here, the derivative of the first component of the Q component is just zero. So this component must be constant. And the other component only depends on this constant. And this is why in this case, the solution is straightforward to write down and is probably the most simple situation that you can imagine. Again, due to this nice structure that the first component just goes to zero and the other one only depends on that one. Good, so we have splitted our model into equations and both of them we solved exactly. And now to obtain a numerical simulation method for the original SDE, we have to combine these two solutions in a suitable way. So there are different possibilities how to combine them. I don't want to talk too much about that. For those who are interested or familiar with this topic, what we use in the following is a so-called Strang composition method, which uses also delta half steps in the composition of the solutions. Good, but instead of going into detail here, I'd like to come to the third part, where we want to use the numerical method that we have just developed to estimate the parameters of our model. So on the one hand, we want to estimate these 0-1 network parameters, the coupling directions. And on the other hand, we also want to estimate continuous model parameters. Like when you remember when I showed you the model, you could see there are also some parameters directly included in the model, as for example, this capital A parameter, which described the amount of activity in a neural population. Good, and we want to estimate these different types of parameters with a simulation-based inference method called approximate Bayesian computation. And in particular, we use an advanced version of this method, which is called sequential Monte Carlo ABC. And we adapted this method that we can deal with the network parameters in a good way. So these network parameters are our main goal to infer. Good, so the algorithm that we finally developed is very long and also contains very heavy notations. So I will not show you this one, but I'd like to give you some idea about the very basic ABC algorithm to introduce you a bit to this method. And then later I will say a few words about the sequential approach that we actually used and also about our contribution in this context. Good, so how does ABC work? So imagine we observe some data. I call this observed data Y. And it could be, for example, a multi-channel EEG data set like the one that I showed you in the beginning. Then we have to assume a prior distribution for our parameter vector. I call the parameters now theta. They contain both the 0-1 network parameters and also continuous model parameters, such as this capital A parameter that I mentioned. Good, and then ABC does the following. So we repeat many times the following procedure. We sample a parameter candidate from our prior. We use this parameter value to simulate a synthetic data set from our model, from our SDE, or actually we simulate the observed component from this SDE. Then we compute some summary statistics from this data set and calculate the distance to the summaries of the observed data set. And then in the end, we keep this sampled candidate also as a sample from the posterior distribution if this distance was small enough. So we kind of collect good values for theta, which in the end represent our posterior distribution. Good, and well, this is, as I said, the very basic algorithm, which is very computationally wasteful, because it samples from the prior distribution throughout, which means a lot of candidates are rejected in the end, for which we have spent a lot of computational effort. So what is typically used or better to use is a sequential approach, which works like this. So it also starts from a prior distribution. So for example, on the left here, you see just a uniform prior for one of the continuous model parameters. So just a uniform over some, let's say, plausible domain for this parameter. And on the right, you also see a prior distribution for one of those 0-1 network parameters. So in the beginning, it's also uniform. Both 0 and 1 are equally likely. Both have probability 1/2. Then we run this ABC method and we construct sequentially intermediate distributions, which through several iterations move closer and closer to the desired posterior that in the end we want to have. Good, and like this it is more efficient, and our contribution in this context was to adjust such a sequential ABC method in order to efficiently account for these 0-1 network parameters. So we introduced some Bernoulli type perturbation kernel. Okay, but no matter which ABC algorithm we use, probably this very basic one, some sequential one, or some adjusted version, the quality of this method will depend a lot on how we choose some of the main ingredients. So the first thing which is very important is the simulation method that we use, because we simulate a lot of synthetic data to which we compare the observed data. So this synthetic data should have a good quality. And I mentioned before that unfortunately for this model, the standard method, the Euler method, is not suitable, which is why we introduced this splitting method that I showed you. So this one we use to simulate the synthetic data. And the quality of the results will also depend a lot on how we choose these data summaries here. And I can maybe quickly show you. So the idea that we had is, instead of using directly the data of this type, we derive several summary functions from these time series data. So these are our summary functions. For example, we derive the density, and to account also for the frequency domain, also the spectral density for each of the individual signals. And then we needed something, of course, to account for possible dependencies among the signals. And there, for example, we also looked at cross correlations as functions of the time lag, or we also considered cross spectral densities. Good, but now I think it's time to show you some results that we obtained with this method. So first, I'd like to show you what we obtained on simulated observed data. So to test the method, we apply it first on simulated data, because then we know the underlying true parameter values that we used to obtain this data, and we can check whether the results that we obtain make sense or not. Good, so this is the data that we observe. We still look at n equal to 4 populations. And now from this data, we want to estimate some continuous model parameters, in particular the 4 A's, which are activation parameters for each of the 4 neural populations. And then we have one coupling strength parameter. And then we also have 12 coupling direction parameters. So these are these 0-1 network parameters. Good, and so we observe this data, we run our algorithm, and now I'd like to show you the results that we obtained for the continuous parameters. So we start with these flat uniform prior distributions. Then we run the algorithm and obtain these blue marginal posterior densities. And here you see as black dashed vertical lines the underlying true parameter values that we use to generate our observed data. And we see that these posterior densities that we obtained nicely cover the true values, and they have a unimodal shape, which is what we were hoping to get. Good, and here are the results for the network parameters, the binary parameters. So for all of them, we start also with a discrete uniform, and then we run the algorithm, and these are the posteriors, which in this example are extremely clear. So here you see as green dashed lines the true parameter values, and we see that we were able to correctly identify all the network connections. So in this example, we had this cascade structure that I also showed you in the beginning. The first population influences the second. So here we have a 1. The second influences the third, and the third influences the fourth. So these 3 are 1, all the others are 0, and we were able to correctly identify this network. Good, so we tested the method also on very different types of networks, and In the end, we applied it also on real EEG data, in particular to this data set that I showed you in the beginning, which you now see here on the right part of this figure. And we applied the method also to the 40 seconds EEG recording directly before the start of the seizures. So we have a before and during seizure scenario. We apply our method on both scenarios, and then we compared the results that we obtained. Good. So these are the results for the continuous parameters. Here we now included a bit more parameters. And well, I will not say too many things here, but just a few observations that we made. So first of all, we see that we obtain very clear shaped posterior densities also for the real EEG data. The blue curves are those that we obtained by applying the method on this seizure data on the right. And the green curves we obtained by applying it on the before seizure data. And looking at this, we see that the results suggest a larger activity in each of the neural populations during seizure. We see it because the posteriors for the A parameters are more on the right during seizure. And we also observe a larger noise intensity during seizure, which we observe by looking at these two panels. The blue curves are again more on the right compared to the green ones. Good. And maybe even more interesting, the results, sorry, I'm not yet done, that we obtained for the binary network parameters. So on the top panel, you see the results for the before seizure scenario, and on the bottom panels, the results for the during seizure scenario. And one thing that we see is that there is a stronger connectivity in the left brain hemisphere when the seizure is happening. We see it, for example, by looking at this RAW2-1 parameter. So before seizure, it was suggested to be not there, because there is a lot more evidence for the 0 value, while during seizure, it is clearly 1. We also see it in these graphs in the bottom. So during seizure, the connection from the second to the first population is not present, while here during seizure, it is clearly present. Good, and another thing we see is that there is less connectivity, for example, from the right to the left hemisphere during seizure and things like that. Good. Yes, this was basically everything I'd like to share with you. Maybe I can say that we also applied the method on other EEG recordings, also from the same patient, and observed a similar behavior. So this could give us some hint about how the brain reacts during and before epileptic seizure. And we also applied it on EEG data of other patients and got some quite promising, interesting results. Good, but with that, I'd like to finish my talk, and thanks a lot for being here and for listening.
Thank you very much, Professor Irene, for your nice presentation. Does anyone have any questions? You can raise your... Okay. Yes, Torben, you can...
Yes, thank you very much for your interesting talk. I have a question. Do you have exchange with the medical community? And what kind of questions are these guys asking you concerning your models and your results?
That's a great question, because I think we really should have, and it's on my to-do list, but at the moment we are not so much in contact with the medical guys. But as I said, it's something I really like to do, and I now also have the possibility to do it because so I started working at the university where I am now in May, and we also have a medical faculty at our university. So this would be very promising, of course, to talk with someone from the medical faculty, but I could not yet do it. But what I know from, I don't know, from my colleagues and so on is that for people in medicine, it's interesting to know these networks that are going on in the brain during seizures. So we knew that this inspired this work, but of course it would be nice to really talk to someone what they in the end need in particular.
Okay, thanks.
Because, of course, you're welcome.
Thank you, Torben, for your question. Does anyone have any questions? If not, I would like to ask you two questions. So you, in the slide before, you show yes. And you say that during seizures, you have this stronger connectivity in the left brain hemisphere than in the right. Do this have any physiological reason why you have this stronger in the left than in the right brain hemisphere?
Well, I think that's exactly what we are hoping to understand from that. Like, so I think often it's very unclear, right, what happens during a seizure and how things react. And with this approach, we are hoping to get some idea for what is going on really in the brain.
Yeah, that's amazing, and it's really useful for medical,
Yeah, I hope
there
so.
should be, yeah, I think there
I
should be
hope
a
so.
reason why, you have this connectivity. Maybe it could be a really nice connection.
Yeah, I think so. I mean, maybe a problem at the moment, as you could see, we restricted the analysis to 4 populations, while EEG is typically measured with more than 60 electrodes, but from computational feasibility, we are far away from these more than 60. So I believe that it can be really helpful, maybe in real life. We have to do a bit more. But the idea was to, I don't know, to see whether it can work. And I believe with what we have here, it could give really some interesting insight in what the brain does during seizure.
Yeah, okay. And my second question, okay, we have a question from the chat. They say, thanks for the presentation, Professor Irene. I was wondering about the stability and uniqueness of the solutions, taking into account the high number of parameters to be tuned.
So as I said, the ST is big, yes, it has high dimensions, but in a way it behaves very nicely from a math point of view because both coefficients are globally Lipschitz, so we know the STE has a unique solution process in the strong sense. And about stability, it's a great question. I did not include it in the talk because there was already so many things. But one can show, or colleagues of mine showed, at least for the one population case, that the STE is geometrically ergodic. So it means the solution converges with exponential speed to a stationary distribution. And this ergodicity property also allows us to, or it can be nicely taken into account when constructing this numerical method. So the Euler method, the standard method, does not preserve this nice ergodic feature, but the splitting method does. So this model is not kind of fascinating from what it describes. It also has some nice mathematical features.
Nice, thank you very much. I would like to ask you something. Maybe we can
Yes.
discuss this later also. So I found that your reformulation of this 6 n-dimensional Hamiltonian type system really fascinating. This really connects this with symplectic geometry.
Yeah,
Because you have
maybe
this
it's similar.
double dimension on the space, and I was wondering if could symplectic structures or this kind of concepts could play a role in these aspects of the dynamics, and then we can have this with SDEs also. It was just a curiosity because I saw this stochastic Hamiltonian type systems, and this is strongly related to symplectic geometry, and I am intersection between these two areas. And I got the curiosity when you introduced this system, this Hamiltonian system.
Yeah, I'm not sure if I can answer the question because I'm not so familiar with this notion of symplectic structure, but I think yes. I mean, I think even this ergodic property that I mentioned is probably such a structural feature, and it is due to this Hamiltonian type structure. So maybe this is exactly one of the links you mean.
Okay, that's really nice. I have to read about it then. Thank you very
Nice.
much, Professor Irene, for your time, for accepting our invitation. And it was really nice to meet you.
Nice to meet you too. Thanks again for the invitations.
Yeah, thank you very much, Professor. So now we have our next talk in 7 minutes.
So maybe I will say goodbye now because I'm not sure how long I can stay.
Yeah,
So
that's okay.
thanks again and all the best.
Yeah, thank you very much.
Bye-bye.
Bye-bye.
tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfeffer.
Welcome back, everyone. For the next session, I am delighted to pass the sharing duties to Yuriko Pitones, who will guide us through the upcoming presentation. Hello, Yuriko.
Hello, thank you, Andrea. Hello, Sara. Good afternoon. After introduce you, can you try share your screen or something?
Yes. Yeah. Oh. Okay, now I think. Oh, sorry, it says that Chrome is not responding, so
Okay, don't worry.
okay, now should be. Oh, wait a second. Oh, sorry, my browser got closed. I don't know why, but just a second. Okay. Okay, now it should be possible.
We see the Zoom, your Zoom.
But do you see my screen? Oh, yeah.
Oh, nice. Okay, let me start with your presentation. It's my pleasure to welcome you to this talk, and it's an honor for me to introduce Zoara Núñez. She began her studies at the Universidad Distrital Francisco José de Caldas in Colombia and obtained her master's degree in mathematics at the Universidad Federal de Amazonas in Brazil. Currently, Zohara is a PhD student in the methods in algebra, arithmetic, and topology group at the Bergische Universität Wuppertal, Germany, and her research focus on algebraic and arithmetic geometry with a particular emphasis on the cohomological properties of wide quotient singularities. In addition to sharing her research, Zohara will also provide her perspective on an important question for our community. What strategies do you think we should take in the mathematical community to make visible the work of famous mathematicians in Latin America and the talent of young women who are building their careers? In this occasion, her talk about cohomology of certain wide quotient singularity. And Zohara, the audience is yours.
Thank you very much, Yuriko, for your introduction, and thank you for the organizers also for inviting me to this beautiful conference. I would say that I am still very naive in many things, so this question is really difficult for me. But up to my short experience, I would say that precisely meetings or conferences like this one are one of the best strategies to make visible the work of women mathematicians, and I would say that by the same line, workshops, schools, little schools that we can make periodically or every year. I don't know, I think like this one, but with a little bit with less formality, such that also the young mathematicians could feel more comfortable and accessible, thinking this like an accessible opportunities. And of course, other thing that I think is completely important is the knowledge dissemination, divulgation. I don't know, the word is still mysterious for me in English, but like journals and things of this type that allowed us to publishing our work. And I would say just one more thing. Collaboration is super important in between women. In between women is a little bit difficult. Sometimes you feel more comfortable speaking with another women professor or colleague. Even more, you feel a little bit that she will understand you. So this is nothing against you men, but sometimes we really need this particular feeling. So I would say this to don't extend my answer. And yes, as Yuriko said, my idea is to talk a little bit today about cohomology of certain wide quotient singularities. And first, I would like you let me try to motivate you about this interesting topic. So I will start explaining a little bit what is this wide quotient singularity. I will give just a feeling of what it is, because usually it's something that intimidates a lot. And it's very difficult, but I will put it in a very chill and relaxed words, such that we can see how our main object of this talk works, and then we see how to continue. So for this talk, I want to fix the following. We're working algebraically closed field such that the characteristic of the field is positive, always in this talk. And for while quotient singularities, I want you to start thinking in a group. In this occasion, in a cyclic group, let's fix it as Z mod PZ, acting in the power series ring in n variables. Sometimes this guy, we will call it R, but for now, just keep it like this, via K-algebra automorphisms. With these K-algebra automorphisms, just thinking in whatever action, I have to be honest, these ones usually are a bit difficult and mysterious. That's why I will not say too much about this, but I can tell you that the quotient singularity can be thinking as the spectrum of this power series ring of them as the invariant ring. With invariant ring, I am speaking when we do the action over the power series ring. And just to be more precise, if Y is spec R, then the quotient arising of this Y with respect to the action is defined. So what I just said, you can picture it like this, and we can call this X, and this will be precisely spec A, where A is this invariant ring. So maybe just to define it a little bit more clear, this A, which are the elements, the invariant elements, are just all the F's which lies here in the power series ring, such that after the action, we again get the same F, and this works for all G in big G. Okay, and in my setup, I want to add another extra assumption, and is that the action is free except in the closed point. So when we say wild to this quotient, the wildness word is making reference to that the P, the characteristic of the field, is dividing the order of the group. Yeah, but our extra assumption will be that we know precisely the bad point, the bad guy of all this history, of all this story, sorry. And wildness usually make us to think that the action is not everywhere free. But in our setting, as I said, we know precisely where this anomaly appears. So with this, I want to do a little bit of history. So let me tell you that Artin in 1975 gave the complete description of this invariant ring for the case n equals 2 and p equals 2. So many people have studied this because it really is the way to classify these quotient singularities. And the nice thing with Artin is that he gave us the precise phase of this hypersurface singularity. So this allowed us to do calculations. And I want to tell you how this looks like. So it is spec A, where A will be the following expression, x, y, z, mod z to the square plus a b z plus y a to the square plus x b to the square, where a and b are elements here also in the power series ring, but in two variables, and they both are co-prime. So as you can see now, we have an explicit expression, so we can play around with this. after this work, one of his PhD students, which also is a woman, I want to say this, Barbara Peskin, in 1983, she gave also a nice description for the case n equals 2, but p equals 3. So the things get a little bit more complicated because the particular thing in these actions is that they are not linear. So the norm and the trace it gets out of control. But with the work of Peskin, let's say that at that point was some hopes that the things could get better. And more recently, Schoer and Lorenzini in 2020, they introduced a new type of action. And of course, the name is, let me give you the name, moderately ramified action. From which arises another type of singularity that I want to share with you today. Oh, sorry. YZ also is a very particular phase of this hypersurface singularity, but with some things that works really different. A to the b, p minus 1, z minus a to the py plus b to the px. Again, a and b are elements in the power series ring in two variables. And today, what we want to focus in is in the particular case where mu is equals 1, a is equals minus y squared, and b is equals to x minus x to the square. Since we are interested into investigate this kind of singularities, we had to find suitable tools for it. And as you can expect, the main tool will be resolution of singularities. So we will speak a little bit about this. And since we want to measure how difficult it is, we want to investigate the cohomology of these blow-ups, which is precisely the higher direct images of the blow-up of the structure shift. So this is what we will do today. This is the big picture. So let me start with an excursion of blow-ups, just to tell you how this machinery of resolution of singularity works in general. And for this, I want to start with a picture. I'm not too good doing pictures, but this is kind of how it looks like. So this this point here is the point that we don't like, where the things don't behave too good. So we want to make it disappear. And the way to do it with our intuition will be to let everything like this, everything the same, less the point. So the point we want to blow it up precisely and make it smooth and with a better behavior. So now let's see how can we do this algebraically. For this, let me define the following. So take a Noetherian ring, take I an ideal, and let me define a tilde as the direct sum of all the powers of this ideal, such that all the powers are graded equals to 0, and I to the 0 will be a. And this is a graded ring, which is the grading multiplication. The multiplication is defined in the following way. And this is what we will call later the blow-up algebra. So I want to give you, let me do a remark, I want to give you some idea how this guy is constructed. So you will take an ideal F generated by these elements. So here, an ideal. And you can build a polynomial ring in R variables, but with coefficients in your ring. And why not? You can construct a phi, a surjective map over this A tilde. So what is the rule of this map? So I can tell you now that you will take monomials here in this graded ring. Remember that a polynomial ring is a graded ring. So you take monomial like this, d to the r, d to the r. Oh, sorry, here is 1. Here is 1. I didn't say this before, but if you have any question, if you want to discuss something, so please don't hesitate. So the rule would be component to component. So what we want really is to track the elements of the A tilde. And since this will be component to component, so as you can hope, you will get things, monomials in this case, in this site, like this. And this is a homomorphism of graded rings, which induces an isomorphism of, this is an homomorphism of graded algebras, which induces an isomorphism of graded rings. How? So you will take this again, your polynomial ring in R variables, and you mod out by this ideal F homogeneous, such that this F applied in F1 to F to the R, it's equal to 0, and this goes to A tilde, where this is an isomorphism, and this guy from here is precisely the kernel of phi. And this is the way how you construct the blow-up algebra. So now we are ready to give our definition. So take X to be an affine scheme, and take I an ideal in A. Yeah. And we want to define X tilde as the blow up of X at the ideal I. And this will be nothing different than the push of A tilde, which goes to X, which is spec A. And this is what we call phi. And we can identify phi minus 1 to the inverse image of this I with E, which is known as the exceptional divisor. So what is the intuition here? That we take points which are singularities, which behaves a little bit bad, and we want to make it in some projective space. This is basically what is happening. And let me complete now this example. This will be our first example, how this works. So you have here, this will be your little point, X, Y, Z. And this will be your equation, X, Y, Z, mod X to the square plus Y to the square minus Z to the square, nothing too terrible. And here your graded ring will be the direct sum of this maximal ideal. Indeed, I can tell you is the maximal ideal here precisely to the n, where n is graded equal to 0. So what we are doing is building a map, which is pi from proche A tilde to spec A. So this is how it looks like. But now let me give you a little bit more interesting example, which is precisely the example that we are interested in today. So we want to compute the resolution of singularities Let me maybe make some quick remark here, just by words, just with my words. So when we talk about resolution of singularities here, we are thinking in a sequence of blow-ups. So, yeah, that's why it's important to define it. And when you blow up your point, probably you can stop and resolve it and get something smooth. But when you have not so nice points, you have to continue blowing up, continue blowing up, continue blowing up, until everything gets smooth. So I will give you the picture with some bad singularity in this talk. So compute the resolution of singularities of the following. So now I want you to remember the first in the motivation when we saw the working of Schoen and Lorenzini, this long equation. So for our particular case will be indeed not the power series ring, but the polynomial ring x, y, z, mod out z to the p minus x to the p minus 1, y to the 2p minus 2z minus x to the p plus 1 plus y to the 2p plus 1. And this is how the guy that we want to treat. So what we have here, we have m, the maximal ideal. So let me tell you little things about the notation. Before in my definition was the ideal I denoted by I, but here I want to denote it by M because precisely because of our assumption at the beginning that the action is free except at the closed point, we know that precisely the point that we want is the maximal ideal. So that's why my notation is like this. So where M is x, y to the z. So how can I know this? Because you just need to apply Jacobian criterion to this ideal, and you will get that the singularity, you will see that the singularity is precisely 0, 0, 0, 0, 0, 0. And the A tilde here, as you can hope, is M to the n greater equal than 0. And what we want is to compute the x tilde, which is the blow up of x at m, which you can also think of this as you can cover all your proche, because here since you have a projective a tilde, approach a tilde, your intuition can say, okay, I can cover all this space with open charts, which is precisely the method. So spec A localize it to 1 tilde. This, you take the 0 parts of this localization and you add the other charts, let's say T2 tilde and the last one, spec A T3 tilde, the 0 part. And this usually is what people call in the literature D plus T to the 1, T to the 2, and T to the 3. Okay, so let me just to give you the feeling how this map looks like. So this is T2, T3, and this goes to the graded blow up, to the blow up algebra, and you send elements like this, nothing too terrible so far, then could get very bad. And then the ideal that you are interested in is given by the literature, by the theory, so which is T1y. I want to give you this because this is really for the computations, minus T2x, T2z minus T3y, T3x, minus T1z, and we are sure that this guy lies in the kernel of phi. So this allowed us to localize, to see what to find precisely where the singularity is. So after doing all these calculations, we will get something like this. And this is x tilde, x1 tilde, x2 tilde, and you continue like this until x tilde p minus 3. So with this, I want to say that we need p minus 3 blow-ups. All this is what we call pi. This is pi 1, pi 2, like this. And this is very interesting because so far is not known resolution of singularities in positive characteristics. So this is a very particular case, but we are sure that we can solve it. Okay, so now with this feeling of a blow-ups, let me go to the third part of this talk, which will be the theorem on formal functions. Okay, so for this, this is a very deep tool, but I will just do a quick introduction and see how can we use it. So you take a projective morphism of Noetherian schemes, and you take F, a coherent sheaf on X, and you take Y, a point. Y, a point in big Y. And you want to define the thickening fiber that I want to denote like Xn, which is X product Y spec OY mod M to the N Y for N greater equal than 1. And this is what we want to call the thickened fiber of X over little y. And how can we picture this? So this guy indeed is a closed immersion here in X, and this goes to Y. This is our F, and here we have spec OY M to the N Y. This is telling us that we are really, everything is concentrated at one point. So by literature, by algebraic geometry, we have that now we want to play with this map, with this, with this Cartesian diagram for one side and for the other side to make it in somehow commute. But now we want to think in higher direct images. So let's call this V, let's call this U, this F prime. So we have that the higher direct images of, so we are taking now what path? This for the other direction and this here. So this is F prime lower star, V upper star of our coherent shift. So this is the pullback, this one is the pullback and this is the push forward. And this, let's say that, okay, so far an isomorphism, we can build an isomorphism. So you take the other direction, the other part of the commutative diagram. So you take F upper star of your coherent shift that now is F, and you take higher direct images, and then you have your push forward, which is U. Yeah. It's not the push forward, it's the pullback, sorry. Here, upper star. And this guy, this will be an isomorphism if and only if this U is flat. But it's not our case. So we don't have this isomorphism because U is not flat in our case, since this is a closed immersion. So after using some identifications of the literature in this situation, we can build a natural map. We can make this, first of all, to be the, since this is concentrated at one point, we can say that these precisely are the global sections of this Xn, Fn, and here we take this, at the end of the day, will be, okay, let me write it, Ri, F lower star F, tensor product OY mod M to the N Y. This is just by definition of the pullback. And after doing this, we do our identification, higher direct images, F lower star F. But now note the following. Note that everywhere we have in somehow everything running in between N. So this means that we can apply, we have direct systems here implicitly, and we can apply inverse limit everywhere. So we have inverse limit here running of N greater equals than 1. And if we apply inverse image inverse limit here, we will get just the completion of the stocks of these higher direct images. So now the theorem and formal functions, what tell us is that this is not just a natural map, but is also an isomorphism. So now this is our main tool, and now the idea is to do an application of this, because remember that what we want to know is information of our singularity. So with this, I want to state the following theorem. I want to maybe do a quick comment. This theorem is due to the following fact. When we did the whole blow up, we realized that we needed to have some tool to give us that allowed us to calculate the higher direct images in every blow up, to do at the end the higher direct images of the whole blow up. So it was too difficult to do it directly. So, but we during the calculations we saw a pattern. After the pattern was we realized that indeed we could generalize this in such a way after get some result, we could calculate immediately the higher direct images for every stage of the blow up, which is this theorem. So let's take AM be local, Noetherian, integral, universally catenary ring such that the dimension of A is equals to R greater equals than 2, and consider K to be this field where M is precisely the maximal ideal given by these elements. But know that here you have something else. You have another element. You have the XR plus 1. And now you want to consider X on a fine scheme, and you want to consider also a blow up, the blow up of X, and you want to say that this has an exceptional divisor E, which lies in PRK of degree D strictly greater than R. So with this, I want to say that the E is the exceptional divisor is really a hypersurface of degree D. Yeah, and now the statement is then the higher direct images. Oh, let me. It is too big. The higher direct images of the blow up, of the structure shift of the blow up, is isomorphic or is equal to 0 if J is not 0 and also is not R minus 1. And we will say that is M if J is equals to R minus 1, where M is a module. M is an A module, and keep in mind that this is an isomorphism of OX modules. M is a priori an M module. Maybe you can just don't abuse of the notation. We do the tilde construction, then we have the OX module. But M without the tilde is an M module of finite length. Finite length, where the length of this thing will be equal to the sum or the summation, I think is the correct way to say, of this binomial coefficient where m is running from m to d minus r minus 1. So let me say just one word about the hypotheses. We need all these hypotheses, universally catenary and integral ring, because we need to be sure of which one is the exceptional divisor that we are taking, and that the dimension respects the rules that we want to play in this game. So now let's try to quickly prove this. So for this, let's consider let's consider the following diagram. So you have E, you have okay. Let me. I think it's healthier to start here. So we have your blow up here. You have your point spec A M, this is your little point, this is spec A, and here this is a Cartesian diagram, so you can do the fiber product, you can do the fiber product here. This is the Cartesian diagram. Recently someone told me that is not like this, but is like this. This is just a funny comment because it is indicating how the maps goes. Anyway, this is what we want to call I, and this is a closed immersion. And remember that since we are interested in the thickening fibers, so we need to recall that the stock, which is indeed equal to the localization at the maximal ideal of this ring, this implicates that now you take this mod out the maximal ideal m to the n at your point, and this will be equal to a to the m mod out m to the n. And this is because we have here an isomorphism which allowed us to do this. So with this, what I want to say here, so now let me modify a little bit this diagram. So instead of have E, you will see that indeed it's E, but when n is equals 1. So you have here, but now the difference is that you want to take here in this spec A mod to the m n. This is the difference. So by the theorem on formal functions, what we have is that the higher direct images of the structure shift of the blow up is isomorphic to the limit of the cohomology of x tilde n f to the n, but now we know our specific shift, which will be indeed O x tilde to the n. And what this means, to be precise, this is the completion, and we have here little x0. So what this is telling us, that we are interested in to calculate this cohomology of the thickening fibers. And the thickening fibers, the intuition is that you build neighborhoods around your point such that you can see how the phenomena behave. Okay, so for this, we want to proceed by induction over n, which n? This one here, this n here. Okay, so when n is equals 1, we want to consider hj x1 tilde OX1 tilde, and this we want to say that is equal to the cohomology of the exceptional divisor and its sheaf. And since we have that this thing here is a closed immersion, let's call it I, we know that we can take this map, the structure sheaf map, I1 lower star OE, and this is just the normal map by definition. And we know that since this is the projective space, this is a hypersurface of degree D, we have that here, this will be the twisted sheaf with minus d, which is the degree of the hypersurface. Then we take cohomology of all this, so we will have a bunch of things here, and also we have a bunch of things here, but we are interested really in the place where we can obtain information of this exceptional divisor, which is precisely in the case we can identify this with the cohomology of the projective space, O to the PR, and here is minus d. So since this is minus d, we know by the cohomology of the projective space that this is a module of a rank that we know, and the rank is precisely some particular binomial coefficient. So by these results, we can say that the length of this module, but indeed hjx1 tilde ox1 tilde, is this will be 0. So you just need to focus in these indexes. It will be 0 if j is in between 1 and r minus 2. Why? This is purely because of the cohomology of the projective space, because we know that when we have the cohomology of something that is different of the dimension of the projective space, that thing will vanishes. Also, we know that when we have negative degrees inside that doesn't coincide with the dimensions, also these things will vanish. So at the end, it will be 0 for particular cases. But we have something when j is equals to r minus 1, and this something is precisely the length of the module, which in this case is d minus 1, d choose d minus r minus 1. Okay, so this was the case d for n equals 1. So now our induction step. So we are not anymore interested in the case where n is equals to 1, but really what we want is this x tilde n. And doing recursively what we just the calculation that we just saw, we have that this will be the same, but here we really have the sum of all the things that we got before. Imagine that we did all together the calculations, d minus n, d minus r minus n. This n, keep in mind that this is the same n here. 2 plus d minus 1, d minus r minus 1, which was the one that we just calculated when r is equals r minus 1. Okay, so with this, now we want to consider the following diagram. So this is phi. Now we have here x to the n, n plus 1 x tilde. And here we have x1, which is indeed the exceptional divisor. And how this goes is spec a to the mod m. This is our point. Spec a m to the n. Spec a m to the m plus 1. And you think in this diagram, and now you have this closed immersion. So we are interested in to analyze this part, which is our induction step. Okay, so we have also, if we are in the level of the rings and not in the scheme setting, we just need to invert all the arrows and see and get the exact sequence from there to go to our next trick, let's say. So now we have I to the n lower star oxn. Here we have oxn n plus 1. And here we know that the kernel of this map is this one, the twisted sheaf of E. And when we apply cohomology, again, we will have a long exact sequence. And this one, we really need to see it carefully. So this is j minus 1, xn to the x tilde n, O x n, J E O E n, H J x n plus 1, O x n plus 1. Here goes again. J, the homology here, but in n, O x tilde n, and H J plus 1. E O E. And this thing continues, but we are interested in this part. So since noted that we need to get information again of this one, but with this thing twisted, sorry, the one that we want is this guy. But to know this guy, we need to investigate this guy. But for the things that we already did before, we can say that the length, and let me call this M, N. So the length of Mn will be 0 if J is in between 1 and R minus 2, and D minus N plus 1. Choose. Yeah?
Yeah, sorry.
Yeah, you have some question?
No, I think it's just a
Okay,
microphone.
okay.
Yeah.
Okay, no worries. So then the trick is to do tensor product with the twisted sheaf O P R K N, but with the first long exact sequence that we got. And okay, I'm sorry that we cannot see the complete thing, but now we the game starts, because for R greater equal than 3, we know that this guy will vanishes, and this guy will vanishes again for the because of results of the cohomology in the projective space. But now we know this guy, this Mn, and we know this one because this is part of our hypothesis induction. And since these are modules, we can get information of this one that is the one that we're interested in. So for if R is greater than equals 3, we can deduce that the length of Hj x tilde n plus 1 O x tilde n plus 1 is precisely 0 again. This will never change. It behaves very, very good. And here the length will be precisely the sum of D plus M with M equals running from 0 to D minus R minus 1 when J is equal R minus 1. Why? Because you just need to do the sum of this, of the N plus Y plus 1 term, then you add to this term this other sum that you have here, then you switch you switch a little bit the limits of the summation, and then you will get these conditions that we are expressing here. Maybe the time is not too long to show you the calculations of this, but if you want, we can explore it a bit more. But just to close the talk, let me tell you the following. Let me tell you that with this we can conclude that when R is greater than equals 3, the inverse limit of H R minus 1 of x n tilde O x tilde n is precisely isomorphic to H R plus 1 x tilde D minus R O x tilde D minus R. So why the inverse limit? Now we take, because if you see in our long exact sequence, here goes n plus 1, then you take 1 and you have the next one, but indeed is 1 less. So you take the inverse limit and you said you conclude that indeed these two are equals, and this is running with from n greater equals 1. And since this is truth, you can say that the length of A of h r minus 1 minus 1 of x tilde d minus r o x tilde d minus 1 minus r is the sum of dm choose m equals to 0, d minus r minus 1. And now more interesting is that, maybe let me put it here, that the higher direct images, this all this thing, since we are concentrated in one point, which indeed is x0, is the completion of all this, and we are concentrated. This is a coherence shift by the Grothendieck cohomology, vanishing cohomology, by the Grothendieck cohomology. Sorry, not vanishing, Grothendieck cohomology. This is a coherence shift supported at one point. We can say that this is the same thing as Ri pi lower star OX tilde, which is indeed the scraper shift. So we have two options: it is 0 or it is something, and precisely is the something in our case is the length of higher direct images, pi lower star OX tilde, which coincides which the length that we wanted to do. And up to my phone, I don't have any more time. So yes, this is the end of the proof, and maybe let me just to summarize. So what do we get with this result? A tool that gives us precise information with for each blow up in the whole sequence of blow ups that we had in the resolution of singularities that we saw in our example, and moreover, we know the precise length of this module. We can think in these higher direct images as indeed this is an AMD minus R module, which a precise length, and this number is giving us how difficult is the singularity in every stage. I think I will stop here. Thank you very much.
Thank you, Sara, for your nice talk. Was very interesting. And now, does anyone have any questions or comments? I have two questions, Sara.
Yeah, please.
In this last theorem, the theorem that you present in the application section, this theorem depends on the characteristic of the field?
This is really general. No,
Okay.
it doesn't. It doesn't depend, and this is precisely the idea to make it as general as possible. So no, it doesn't depend.
Okay, thank you. And the other question is, this approach use the classical method for resolving singularities and the blow-ups. And so can these ideas apply other methods? Resolution via Nash, blow-ups of Nash, or for instance?
Okay, the easy question, the quick answer should be I haven't tried, so I don't know. But I think it should be possible, at least as I know. The work of Schor and Lorenzini, they did it with similar strategy, but they used the fact that we were in in the power series ring. So with this power series ring, they what they did was to arrive after two normalizations, that maybe I forgot to say this. And after these two normalizations, they expressed the singularity in such a way they could jump to another well-known singularity, and they used the Jung method of resolution of singularities. And indeed, the last Tuesday, I couldn't attend, but I saw a talk about one professor in Versailles who developed the method, the Jung method, indeed, for whatever positive characteristics. So it will be very interesting to see if it could be easier, because indeed, with this method, it was really long.
Yeah.
But yeah, but it's possible. I think it would be a very good exercise to try another methods.
Okay, thank you. Thank you. We have a question in the chat by Lamine. The question is, can you use cohomology as you have done in PDS? And who appears the blow up here? Because I know we can use index theory in this area. Thank you for your response.
Oh, thank you for your question, but I should be honest. I don't know the methods. Oh, hello. Okay,
Yeah.
sorry. I think sorry, and I don't know. Can we use cohomology as you have done in? This is differential equations, right? No, I don't know. No, I don't know. Maybe again will be a good exercise to try it, but I don't know. As this, yes, I don't have too much to say in this.
Okay. Okay. Thank you. And I want to read this comment of the chat. Valentina Martinez say, thank you for your presentation. And above all, you're showing the importance for women in mathematician that can do science. Congratulations.
Oh, thank you, Valentina.
Thank you for your presentation. Any question or comments for Suara?
In relation with category, said Lamine. We shouldn't explore. I don't know.
No.
Thank you for your questions and for your comments.
Okay, congrats. Thank you, Sara, for accepting our invitation, and it was a pleasure heard your talk and your answer to the question in this event.
Thanks to you. Thanks a lot to the organizers again and to all the participants.
Okay, now we have a break. Thank you for attending this first session of the day, and we will resume at 5 p.m. Central European time. Yes, 5, right? Okay.
Latin American Woman Mathematician, aprobado en febrero de 2020. El proyecto Visibility of Latin American Woman Mathematician, aprobado en febrero de 2024 por el Committee for Women in Mathematics of the International Mathematical Union, busca visibilizar a mujeres matemáticas de Latinoamérica entre grupos de niñas y jóvenes de escuelas rurales, con el fin de concientizar que, sin importar fronteras, las mujeres matemáticas realizan grandes contribuciones en la ciencia y la industria. El objetivo es impulsar modelos femeninos a seguir en las carreras STEM y principalmente en matemáticas, para que las niñas de hoy y las mujeres del mañana tengan mayores posibilidades de alcanzar sus metas y aspiraciones, considerando como una posibilidad ser científicas.
Me acuerdo que en mi salón de clases de la primaria, al menos la mitad de los estudiantes éramos niñas. Luego en la secundaria, preparatoria y en la universidad, la proporción aumentó. De hecho, en mi generación de licenciadas en matemáticas, nos graduamos solo mujeres. Pero cuando pienso en el terreno de las ciencias y las matemáticas, me pregunto, ¿cuántas mujeres se desempeñan profesionalmente? Las cuentas no me cuadran. No recuerdo que en mi niñez me hayan acercado especialmente a las matemáticas. El entorno escolar no me preparó para indagar en el terreno académico y matemático. Si pienso seriamente, no encuentro los caminos ni las vías que me han traído hasta aquí. Tal vez me convertí en matemática por casualidad. Lo cierto es que fue y es una fortuna, porque si me transportara al contexto escolar en el que crecí, debería estar haciendo algo distinto. Lo que he dicho hasta ahora no es una queja ni un reclamo, sino una reflexión sobre lo que acontece en la escuela. El sesgo no solo ocurre en la formación académica, también en el entorno familiar y social. ¿Por qué pasa esto? Quizá porque se piensa que las matemáticas y las ciencias solo pueden ser practicadas por hombres, como los deportes, y entonces, por omisión, somos descartadas como futuras matemáticas y científicas. Nadie nos impulsa ni se ocupa de revelarnos que podríamos dedicarnos a las matemáticas, astronomía, física, química, medicina. Según un estudio de la Organización de las Naciones Unidas, en 14 países, la probabilidad de que las mujeres obtengan un grado de licenciatura es del 18%, 8% para un grado de maestría, y solo el 2% logra un título de doctora en alguna materia relacionada con la ciencia. La representación de mujeres en las carreras científicas es del 28%, frente al 72% de los hombres. ¿Qué tenemos que hacer para que estos números y nuestras realidades cambien? No tengo la respuesta, pero estoy segura de que la sociedad en todos sus niveles debe motivar el desarrollo científico en las niñas. Debemos hacerlo para no seguir desperdiciando el talento y las ganas de niñas y jóvenes. Así, en el futuro, podremos tener una ciencia vasta, gigante y más justa. Desde donde estamos, un grupo de mujeres matemáticas latinoamericanas buscamos impulsar y motivar a las niñas a ser científicas. El mensaje es claro y sencillo. Es importante conocer y reconocer a las mujeres matemáticas que se desempeñan profesionalmente hoy en día, que sean mentoras y modelos a seguir. Pero es más importante que nuestro mensaje llegue a todos los rincones de nuestro país. Cuando les preguntamos a las niñas ¿a cuántas mujeres científicas conocen? Algunas responden Marie Curie, y es que Marie Curie es nuestra heroína. Pero cuando les preguntamos ¿a cuántas mujeres matemáticas conocen? Hay un silencio prolongado y miradas buscando respuesta unas con las otras. Si hoy volvemos a hacer esta pregunta, las niñas con certeza responderán.
Hola, soy Yadira Valdivieso, soy matemática mexicana y hago teoría de representaciones.
Hola, ¿qué tal? Soy Verónica Redondo y actualmente trabajo también para el Senado de la República en la Secretaría Técnica de la Tesorería.
Hola, soy Ruth Alejandra Torres, matemática colombiana. Actualmente soy directora del programa Matemáticas de la Conrad Lorenz en Bogotá, Colombia.
Soy Rosibel Pacheco, matemática hondureña, presidenta de la Asociación Matemática de Honduras.
Soy Rita Jiménez Royand, matemática mexicana y soy investigadora en el área de topología algebraica.
Hola, ¿qué tal? Soy Raquel Perales, soy una matemática mexicana y mis áreas de investigación son la geometría riemanniana y el análisis geométrico.
Hola, soy Pati Jiménez, soy matemática mexicana, trabajo en la Universidad Autónoma de Zacatecas.
Hola, me llamo Pamela Estefanía Harris, nací en Guadalajara, Jalisco, México y he vivido en Estados Unidos desde los 12 años. Soy matemática y mi investigación se enfoca en la combinatoria algebraica.
Soy Nancy Gelman, matemática de nacionalidad argentina y trabajo en Uruguay hace muchos años. Me dedico a los sistemas dinámicos y acciones de grupo.
Soy Marta Reynoso, soy una matemática mexicana. Mi área de estudio es la teoría algebraica de números, pero también me interesan la historia y la divulgación de las matemáticas.
Hola, soy Marta Álvarez, soy matemática que trabajo en Guanajuato.
Hola, soy María Isabel Cortés, matemática chilena y trabajo en las áreas de sistemas dinámicos y teoría de grupos.
Hola, soy María Chara, soy docente e investigadora de CONITEC en Argentina, la Universidad Nacional del Litoral, y me dedico a la teoría del código.
Soy Luz María García Ávila, matemática mexicana e investigadora en el área de teoría de conjuntos.
Hola, soy Leticia Brambila Paz, mexicana, trabajo en geometría algebraica, en particular en espacios módulos sobre haces vectoriales.
Soy Leslie Campa Raimundo, matemática mexicana. Soy investigadora en el área de mecánica celeste, particularmente en configuraciones centrales.
Soy Laura Rocío González Ramírez, matemática mexicana y soy investigadora en el área de matemáticas aplicadas a biología y medicina.
Hola, ¿qué tal? Mi nombre es Isabel Hernández. Soy matemática mexicana y mis áreas de investigación son el álgebra no asociativa y la teoría del libro.
Soy Gabriela Jerónimo, matemática argentina. Trabajo como profesora e investigadora en la Universidad de Buenos Aires y en el CONICET en el área del álgebra computacional.
Soy Gabriela Araujo, soy matemática, trabajo en el Instituto de Matemáticas de la UNAM, en la unidad Juriquilla y me dedico a la combinación.
Hola, soy Elizabeth Gasparín, brasileña que trabaja en Chile y me dedico a la investigación en geometría.
Hola, mi nombre es Edith Mireya Vargas García. Soy mexicana, profesora del Departamento de Matemáticas del ITAM. Mi área de especialidad es álgebra universal.
Hola, soy Diana Bueno, matemática colombiana y trabajo en teoría de códigos, que es el área de las matemáticas que ayuda a entender el proceso de comunicación de manera fiable.
Hola, me llamo Claudia Reynoso Alcántara. Soy una matemática mexicana. Trabajo en la ciudad de Guanajuato, en México, y mi área de investigación es la teoría de foliaciones y la geometría algebraica.
Soy Carolina Úrsula Torres, matemática chilena, y soy investigadora en el área de análisis numérico.
Soy Carolina Mosquera, matemática argentina, docente en la Universidad de Buenos Aires e investigadora en el CONICET en el área de análisis armónico.
Olá, eu me chamo Andressa Gomes, sou brasileira e pesquisadora matemática. Atuo na área de equações expressivas e atualmente ocupo a posição de pós-doutorado na Universidade Federal do Piauí.
Soy Analía Silva, matemática argentina, trabajo en la UNSL y en el IMASEL y me dedico a las funciones diferenciales.
Hola, soy Amanda Montejano Cantorá, matemática mexicana. Soy investigadora en el área de teoría de números combinatoria, teoría de Ramsey y teoría extremal de gráficos.
Soy Alisa Wittgenstein, soy una matemática argentina, investigo en el área de geometría algebraica y aplicaciones. Desde fin de mes seré la presidenta de la Academia Nacional de Ciencias Exactas, Físicas y Naturales en mi país.
Hola a todas, soy Alexandra García, matemática en máster en Ciencias Actuariales y Financieras. Actualmente trabajo como actuaria regional en Allianz Trade, una compañía de seguros.
¿Ya estás grabando? ¿Sí? Sí. Bueno, como te decía, estamos haciendo el recuento de los hechos y la verdad es que este proyecto ha traído para mí mucha reflexión, mucha satisfacción, porque me ha permitido colaborar con muchas personas y con muchas instituciones. Quiero aprovechar para dar las gracias a todas las mujeres latinoamericanas que enviaron su video con un mensaje inspirador para las niñas y jóvenes. También quiero aprovechar para agradecer a todas las instituciones, a todo el personal administrativo y técnico, porque juntos hemos hecho que este proyecto sea una realidad. En particular, quiero agradecer a la Escuela Primaria Ignacio Zaragoza y a la Escuela Secundaria Técnica número 47 de la comunidad de Lobatos, Valparaíso, Zacatecas, a sus autoridades educativas, a los padres y madres de familia por sus autorizaciones y muy especialmente a las niñas y jóvenes por abrirnos las puertas de sus aulas, por permitirnos llevar este proyecto. Un video con un mensaje de muchas mujeres matemáticas, un mensaje inspirador y motivador. Hemos cumplido el objetivo. No fue difícil elegir el lugar donde llevaríamos este proyecto, porque yo también fui una de esas niñas que no consideraba las matemáticas como una profesión. Hoy, desde la posición en donde estoy, asumo mi rol y la responsabilidad que eso conlleva. Y estoy segura que, al igual que yo, muchas mujeres matemáticas seguiremos impulsando y promoviendo iniciativas para motivar la participación de más niñas y jóvenes en la ciencia y en las matemáticas.
Hemos sido amigos y colegas por mucho tiempo. Nuestro mayor logro, primero, poder formar un equipo de univallunos y segundo, poder establecer estas alianzas poderosas y que de alguna u otra forma visibilizan el talento matemático de Colombia en el mundo.
Mi nombre es Brian Grajales, soy egresado del programa de matemáticas de la Universidad del Valle y actualmente me encuentro haciendo una estancia postdoctoral en la Universidad de Campinas, en Brasil.
Mi nombre es Duan Cardona, soy egresado del programa académico de matemáticas de Univalle y actualmente soy investigador asociado del Centro de Análisis y Ecuaciones Diferenciales en Bélgica.
Con mi colega Duan tenemos nuestra organización ICMAM Latin America, que busca la conexión entre diferentes centros de investigación, entre diferentes investigadores jóvenes y expertos de todo el mundo a través de conferencias virtuales organizadas cada 2 años.
Nuestra empresa ICMAM Latin America tiene 3 objetivos fundamentales. El primero, acortar la brecha que existe entre la interacción de jóvenes investigadores latinos con expertos internacionales. Segundo, publicar el trabajo científico de estos jóvenes. Y tercero, visibilizar el trabajo de las mujeres en las matemáticas.
Ser egresado de la Universidad del Valle es algo muy bonito y significa tener siempre un deber con la sociedad, estar siempre al servicio de la comunidad.
A un egresado de la Universidad del Valle lo caracteriza su integridad, su ética, su interdisciplinariedad, su capacidad de trabajo en equipo, de liderazgo y sobre todo de excelencia.
Soy egresado.
Soy Univalle.
En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
Hola, soy Jessica, soy mexicana y soy estudiante de maestría en matemáticas. En algún momento de mi vida fui como tú, una niña, una joven que cursaba la primaria, la secundaria y la preparatoria. Cuando somos pequeños es muy difícil imaginar qué será de nuestras vidas. También es difícil reconocer nuestras capacidades y nuestros gustos. Y conforme crecemos, tomar decisiones sobre nuestro futuro se vuelve cada vez más necesario e importante.
Hola, yo soy Miriam, también soy mexicana y estudiante de maestría en matemáticas. En algún momento de mi vida también fui como tú. Cuando tenía 15 años, las matemáticas me empezaron a gustar cuando un profesor me las empezó a explicar con un gran entusiasmo.
Cuando somos jóvenes, aún con las matemáticas que nos enseñan en la escuela, esta disciplina sigue siendo un mundo desconocido, que cuando te apasionan tanto, es muy emocionante entrar en él y descubrirlo.
Hoy te queremos presentar a algunas mujeres matemáticas latinoamericanas que desarrollan su investigación en diferentes áreas. Tal vez escuches palabras desconocidas, para mí también lo fueron. Te invito a conocerlas.
Hello, Jess. ¿Estás lista para saber qué les dirían a ellas? Empecemos.
Hola, soy Yadira Valdivieso, soy matemática mexicana y hago teoría de representación.
Hola, ¿qué tal? Soy Verónica Redondo y actualmente trabajo también para el Senado de la República en la Secretaría Técnica de la Tesorería.
Soy Silvia Jerez, matemática española y trabajo en CIMAT, México. Mis áreas de investigación son análisis numérico y ecuaciones diferenciales parciales con aplicaciones a biología y dinámica de fluidos.
Hola, soy Ruth Alejandra Torres, matemática colombiana. Actualmente soy directora del programa Matemáticas de la Conrad Lorenz en Bogotá, Colombia.
Soy Rosibel Pacheco, matemática hondureña, presidenta de la Asociación Matemática de Honduras, asociación no gubernamental de desarrollo que está comprometida con el mejoramiento y la excelencia en la enseñanza de la matemática y en que los jóvenes todos los días estén conscientes que la matemática aporta al desarrollo de un país de manera significativa.
Soy Rita Jiménez Royand, matemática mexicana y soy investigadora en el área de topología algebraica.
Hola, ¿qué tal? Soy Raquel Perales, soy una matemática mexicana y mis áreas de investigación son la geometría riemanniana y el análisis geométrico.
Hola, soy Pati Jiménez, soy matemática mexicana, trabajo en la Universidad Autónoma de Zacatecas y yo les diría a las niñas y jóvenes que las matemáticas son fascinantes, son divertidas y están llenas de retos para todos ustedes.
Hola, me llamo Pamela Estefanía Harris, nací en Guadalajara, Jalisco, México y he vivido en Estados Unidos desde los 12 años. Soy matemática y mi investigación se enfoca en la combinatoria algebraica.
Soy Nancy Gelman, matemática de nacionalidad argentina y trabajo en Uruguay hace muchos años. Me dedico a los sistemas dinámicos y acciones de grupo. Y bueno, yo diría, las invito a las chicas a hacer matemática porque es algo muy divertido, es como jugar, como un mundo muy fascinante. Prueben, es muy lindo y muy divertido.
Hola, soy Marta Bermúdez, soy una matemática mexicana. Mi área de estudio es la teoría algebraica del lenguaje. Pero también me interesan la historia y la divulgación de las matemáticas.
Hola, soy Marta Álvarez, soy matemática que trabajo en Guadalajara, me dedico a las matemáticas aplicadas y en este mensaje quiero decirle a las niñas, jovencitas que estudien matemáticas que les permitirá poder describir parte del mundo a través de ecuaciones diferenciales, por ejemplo, y de matemáticas.
Hola, soy María Isabel Cortés, matemática chilena y trabajo en las áreas de sistemas dinámicos y teoría de grupos.
Hola, soy María Chara, soy docente e investigadora de CONICET en Argentina, la Universidad Nacional del Litoral, y me dedico a la teoría del código.
Soy Luz María García Ávila, matemática mexicana e investigadora en el área de teoría de conjuntos.
Hola, soy Leticia Brambila Paz, mexicana, trabajo en geometría algebraica, en particular en espacios módulos sobre haces vectoriales.
Soy Leslie Campa Raimundo, matemática mexicana. Soy investigadora en el área de mecánica celeste, particularmente en configuraciones centrales.
Soy Laura Rocío González Ramírez, matemática mexicana y soy investigadora en el área de matemáticas aplicadas a biología y medicina.
Hola, ¿qué tal? Mi nombre es Isabel Hernández. Soy matemática mexicana y mis áreas de investigación son el álgebra no asociativa y la teoría del hilo.
Soy Gabriela Jerónimo, matemática, argentina. Trabajo como profesora e investigadora en la Universidad de Buenos Aires y en el CONICET, en el área del álgebra computacional.
Soy Gabriela Araujo, soy matemática, trabajo en el Instituto de Matemáticas de la UNAM, en la unidad Juriquilla y me dedico a la combinación.
Soy Fuensanta Roca, matemática española, y soy investigadora en teoría de singularidades y geometría tropical.
Hola, soy Elizabeth Gasparín, brasileña que trabaja en Chile y me dedico a la investigación en geometría.
Hola, mi nombre es Edith Mireya Vargas García, soy mexicana, profesora del Departamento de Matemáticas del ITAM, mi área de especialidad es álgebra universal y a las niñas y jóvenes, si desean saber cómo codificar o decodificar mensajes, en las matemáticas encontrarán la respuesta. Y recuerden que las matemáticas no distinguen género y su estudio no es exclusivo para los hombres.
Hola, soy Diana Bueno, matemática colombiana y trabajo en teoría de códigos, que es el área de las matemáticas que ayuda a entender el proceso de comunicación de manera fiable.
Hola, me llamo Claudia Reynoso de Cántara, soy una matemática mexicana. Trabajo en la ciudad de Guanajuato, en México, y mi área de investigación es la teoría de foliaciones y la geometría algebraica.
Soy Carolina Ursula Torres, matemática chilena, y soy investigadora en el área de análisis numérico.
Sí. Soy Carolina Mosquera, matemática argentina, docente en la Universidad de Buenos Aires e investigadora en el CONICET en el área de análisis armónico.
Olá, eu me chamo Andressa Gomes, sou brasileira e pesquisadora matemática. Atuo na área de equações expressivas e atualmente ocupo a posição de pós-doutorado na Universidade Federal do Piauí.
Soy Analía Silva, matemática argentina, trabajo en la UNSL y en el máster y me dedico a las funciones diferenciales.
Hola, soy Amanda Montejano Cantorá, matemática mexicana. Soy investigadora en el área de teoría de números combinatoria, teoría de Ramsey y teoría extremal de gráficos.
Soy Alicia Wittgenstein, soy una matemática argentina, investigo en el área de geometría algebraica y aplicaciones y desde fin de mes seré la presidenta de la Academia Nacional de Ciencias Exactas, Físicas y Naturales en mi país.
Hola a todas, soy Alexandra García, matemática en máster en Ciencias Actuariales y Financieras. Actualmente trabajo como actuaria regional en Allianz Trade, una compañía de seguros.
Hemos presentado mujeres que algún día también fueron niñas y jóvenes como tú, que poco a poco desarrollaron un gusto por la ciencia y las matemáticas, convirtiéndolas en su profesión. Ojalá que después de conocerlas, al igual que yo, digas, un día quiero ser como ella.
¿Qué te pareció? Impresionante, ¿cierto? Todas ellas son una parte de las mujeres matemáticas en Latinoamérica y al igual que nosotras, tú puedes ser parte de ellas.
Es importante conocer mujeres científicas, mujeres matemáticas que están activas en estos tiempos, pues es una forma de inspirarte y ojalá que en ellas y muchas otras mujeres encuentres modelos a seguir.
Jessica, quiero preguntarte, ¿qué le dirías a una niña o una joven para motivarla a estudiar una carrera científica o matemáticas?
Yo les diría que si les gusta alguna materia de las ciencias, química, física, matemáticas, puede llegar a ser un poco difícil, pero paso a paso van a seguir creciendo y verán que esto es muy divertido, que vale la pena, que es cumplir un sueño más y que no se dejen llevar por algunos comentarios que pueden pensar que es imposible. Entonces lo más importante es cumplir un sueño. ¿Qué les dirías tú?
En el mundo de las ciencias exactas son muchos mundos por descubrir, muchos temas que conocer y siempre tener una meta y ver que con el tiempo se puede llegar a cumplirlos. ¿Quieres saber qué te dirían ellas?
Yo le diría a las niñas, a las adolescentes, a todas las mujeres que estudiar ciencia, estudiar matemáticas te abre infinitas posibilidades porque básicamente estudiar matemáticas es estudiar un lenguaje universal.
A las niñas y jóvenes les diría que descubran qué es lo que les gusta y si lo que les gusta es pensar y resolver problemas, la ciencia es una muy buena opción.
Las matemáticas son una actividad creativa y como todo espacio creativo, es muy importante fomentar en ellas la diversidad. Como matemática y como presidenta de la Sociedad Matemática Mexicana en este momento, invito a las jóvenes y en general a los grupos subrepresentados en las carreras STEM a unirse con nosotras para crear espacios matemáticos llenos de gusto, de respeto y de disfrute.
Y quiero decir a las jóvenes que están considerando juntarse a hacer trabajo de investigación en matemáticas, que la investigación es un trabajo bonito, es divertido, y cuando encuentras alguna cosa completamente nueva, se tiene un sentimiento realmente hermosísimo, por lo que pues únanse a nosotros.
Hoy quiero invitar a las niñas y las jóvenes para que se dejen maravillar por las matemáticas y por todo lo que con ellas se puede hacer para construir un mundo mejor. Que las exploren, que se diviertan con ellas y que si les llaman la atención, las estudien, para que en un futuro seamos colegas.
Si eres una niña joven, curiosa, con imaginación y que le gusta crear o descubrir cosas nuevas, sigue así. El mundo necesitará tus talentos quando seas grande.
Eu tenho a dizer a você, mulher, que gosta de estudar matemática e possui espírito investigativo, que não deixe de aproveitar as oportunidades que existem em seu país, que incentivam as mulheres a ingressarem e permanecerem nessa carreira.
A las niñas y jóvenes que les da curiosidad el mundo de las matemáticas o que les interesa alguna carrera afín a estas, pues les diría que se atrevan a conocerlas, que el pensamiento matemático nos proporciona mucha libertad y muchas satisfacciones también. Que persigan sus sueños, que confíen en sus intuiciones y que se acerquen a la comunidad de mujeres matemáticas.
Te diría que si estudias matemática puedes ser quien quieras ser. Desde científica trabajando en investigación, como matemática trabajando en ingeniería e inclusive puedes trabajar en la bolsa de valores en economía.
Las matemáticas son un arte y nos dan muchísima oportunidad de ser creativas. Tú sabes, las matemáticas son importantes en todas las ciencias. Quiero que trabajes fuerte, busques muchos mentores y con tu dedicación vas a llegar muy lejos. Y en el camino asegúrate de disfrutar tus logros y ayudar a otra gente. Te deseo lo mejor.
En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos, nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
Somos el cuerpo efímero, pero gracias a las matemáticas, nuestras ideas trascienden la mortalidad. Simbólicamente, las mujeres hemos sido relacionadas con el campo emocional, el cuerpo físico y la intuición, separado del hombre al que se le han atribuido características más intelectuales, relacionándolos con el mundo de las ideas y la toma de decisiones políticas con cabeza fría. Sin embargo, a lo largo de la historia, la humanidad se ha beneficiado de los hallazgos que miles de mujeres científicas han aportado a la sociedad. Por esto, desde el ISAAC-ICMAM Latin America, construimos una comunidad matemática inclusiva, respetuosa e inspiradora, que conecta a las mujeres matemáticas con entornos académicos internacionales, para visibilizar su trabajo y potenciar sus habilidades. Algunas de las mujeres líderes en matemáticas de nuestra institución son Karina Navarro González, Jessica González Hurtado, Yuriko Pitones, Marlisha Sandoval, Alexandra García Medina y Ruth Alejandra Torres Rubiano. Nos interesa aportar a un mundo más equitativo y justo, donde sin importar el género, las fronteras geográficas y económicas, todos y todas tengan la oportunidad de desarrollar una carrera exitosa en las ciencias matemáticas y contribuir al desarrollo humano y social. ICMAM Latin America, el lugar donde las matemáticas transforman el mundo.
En el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos. Nosotros somos ICMAM Latin America, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latin America nos dedicamos al fomento de su investigación, con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020, celebramos la primera edición del evento, y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia, y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones, los acercamos a congresos y bienales en diferentes países, creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latin America, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades, hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
Hemos sido amigos y colegas por mucho tiempo. Nuestro mayor logro, primero, poder formar un equipo de univallunos y segundo, poder establecer estas alianzas poderosas y que de alguna u otra forma visibilizan el talento matemático de Colombia en el mundo.
Mi nombre es Brian Grajales, soy egresado del programa de matemáticas de la Universidad del Valle y actualmente me encuentro haciendo una estancia postdoctoral en la Universidad de Campinas, en Brasil.
Mi nombre es Duan Cardona, soy egresado del programa académico de matemáticas de Univalle y actualmente soy investigador asociado del Centro de Análisis y Ecuaciones Diferenciales en Bélgica.
Con mi colega Duan tenemos nuestra organización ICMAM Latin America, que busca la conexión entre diferentes centros de investigación y entre diferentes investigadores jóvenes y expertos de todo el mundo a través de conferencias virtuales organizadas cada 2 años.
Nuestra empresa ICMAM Latin America tiene 3 objetivos fundamentales. El primero, acortar la brecha que existe entre la interacción de jóvenes investigadores latinos con expertos internacionales. Segundo, publicar el trabajo científico de estos jóvenes. Y tercero, visibilizar el trabajo de las mujeres en las matemáticas.
Ser egresado de la Universidad del Valle es algo muy bonito y significa tener siempre un deber con la sociedad, estar siempre al servicio de la comunidad.
A un egresado de la Universidad del Valle lo caracteriza su integridad, su ética, su interdisciplinariedad, su capacidad de trabajo en equipo, de liderazgo y sobre todo de excelencia.
Soy egresado.
Soy Univalle.
Good afternoon, everyone. It's a pleasure to continue with our engaging lineup of speakers. Our third speaker today is Dr. Laura A. Miller, a professor of mathematics at the University of Arizona and an adjunct professor in biomedical engineering. Dr. Miller is a distinguished mathematical biologist whose groundbreaking research explores the biomechanics of fluid dynamics in nature, including insect flight, jellyfish propulsion, and embryonic heart blood flow. Today, she will present her talk on flows around some species of soft corals. Before we dive in, Dr. Miller's talk, could you share with us how did you become interested in mathematics? At what point in your life did you decide to become a mathematician? Welcome, Professor Miller.
Okay, I was muted. Thank you. I have to apologize. I'm at home. This is Thanksgiving morning in the US, which is a holiday here. So no problem, but you might hear some dogs in the background.
Thank you very much for attending in Thanksgiving. That's an honor for us.
So I have a couple of slides just because the answer to that question for me is a little bit complicated. And I want to go back to when I started as a student. I grew up in Ohio and West Virginia in a very small town. And for undergrad, I went to the University of Chicago and started as a math major. But, there were several reasons why I didn't stay a math major. I think at the time, I didn't think I wanted to prove theorems as a career. But I think also my background hadn't prepared me to be a math major at a university like Chicago. And I also felt a bit isolated. At the time, I was the only woman in many of my classes, and there weren't women professors who were tenure track at Chicago. So I switched to biology, which I also love, and I did experimental research on horseshoe crabs. But I missed mathematics, and at the time in biology, there was very little math that was applied. So it was, either do math or do biology, and that's it. So I went on to do a master's at Duke University. I started a PhD program in zoology. And because I was interested in biomechanics, I started taking math and engineering again. And I met people who were doing mathematical biology, which I thought was really quite interesting. And I wanted to apply computations to problems in biomechanics. And at some point, I realized that not having a strong background in mathematics was going to hold me back. And I started to look into going into a PhD program in mathematics from zoology, which is not very common, not super easy to do. But I did go to NYU, the Cron Institute, and got a PhD in math. I worked with Charlie Peskin, who started out in an MD PhD program as he wanted to become a medical doctor. And so he was a great advisor because, like me, he had started in the life sciences and then developed a love for mathematics afterwards. So since then, I'm now at, well, I'll skip that in the interest of time, but I'm at University of Arizona now. I've been in biology departments as a faculty member and in mathematics and now in BME. So I go back and forth between the two fields. There are things that I love about both. So I thought I'd just give a little more history because the answer to that question for me is complicated. So I answer all the questions?
Yes, Professor. Thank you very much.
Mm-hmm. And at the end, I'm happy to answer any questions about what that was like making the transition and why. But for my talk, I think this is a good transition because my talk is based in both mathematics and biology, working with collaborators from marine biology as well as engineering and physics and oceanography. So I am on the very applied side of mathematics, I would say. I publish in math biology journals, but also in just pure life science journals, engineering journals, and so forth, and work with students from all these fields. So I'll highlight a little bit of one of the applications we've worked on, which is looking at fluid flow around some soft corals. All right, so I'm going to talk first a little bit about the effective scale and dimensionless numbers. And then I'm going to talk about the mathematical tool, the computational tool that we use to look at these types of problems, and then look at two example applications. So filter feeding by sea fans, which are pictured here, as well as nutrient exchange in pulsing corals. And so obviously coral reefs are very important to the ocean ecosystem. There's a huge range of morphologies. They're quite complicated. They have to interact with the ocean environment. They have to withstand hurricanes. They have to withstand scuba divers and boats, perhaps colliding with them at times. They have to interact with their environment and capture food. They have to exchange gases and also remove waste. And all of them do it in different ways. Some corals are doing better than others with the effects of humans. So sea fans are doing quite well, I would say, which is one of the reasons why I'm going to start off talking about them. And just for some orientation, so this is what the sea fan looks like from far away. So it looks like a fan. If you zoom into these branches, you can see polyps that emerge from the sea fan. They're actually animals. They have muscles, and they capture little plankton, copepods, other small organisms, and feed on them. They also have symbiotic algae that photosynthesize, and they take some of the energy from those organisms. So one question that you might ask is why study fluid dynamics and biology and mathematics? And there's a whole range of applications. I've worked on a few of them, but a much more vast area as well. Going from the cellular scale, which you can see here, So this is an old simulation from my postdoc advisor of blood platelets, and the flow is going from left to right. And when they're activated, they bind together and form a clot. And so as the clot is forming, it starts to slow the flow. And it's quite a complicated interaction where you have some biochemistry, solid mechanics, and fluid dynamics, all being involved in this process of forming a clot. You can also look at larger scales and think about aerodynamics. So this is a bird chase. One bird is chasing another out of its territory, and they make very complicated maneuvers that our micro air vehicles are not quite able to perform at this level. So looking at the aerodynamics of bird flight is also quite a complicated problem, and computational fluid dynamics is used, but it's challenging, and I'll go into some of the reasons for why it's challenging as well. So as I go through my two applications, I just want to mention that my lab combines some field work with mathematics. And we have a saltwater system for invertebrates, corals, and jellyfish that is in the lab at U of A. We also go to Key Largo, to the Key Largo Marine Lab, and look at animals in the ocean. And there are quite a few differences there that in terms of mathematical modeling are important. The organisms deal with forces and interactions that are quite different than in the lab. And we also have a number of flow tanks that we use to recreate currents. And so you'll see some results from these different areas as I go along. Okay, so let's talk a little bit about the mathematics of fluid dynamics and the Reynolds number, which is one of the first important dimensionless numbers I want to mention. So the Navier-Stokes equations describe fluid motion, that being air or water. It's a nonlinear system of partial differential equations. It basically boils down to F equals ma. So if you take a little parcel of fluid and you look at the acceleration of that particle times its mass, it's going to be equal to forces that are acting on it. So pressure gradients, viscous dissipation, and any sort of external force being applied to it, perhaps from a moving fin or an obstacle or something like that. If you non-dimensionalize the equations using a characteristic length scale, which let's say for a jellyfish, or it might be the width of the jellyfish bell, times a characteristic velocity, and that might be the swimming speed, times the density of the fluid over the dynamic viscosity or the stickiness of the fluid. And this gives you the ratio of inertial to viscous forces in the fluid. And flows of the same Reynolds number are dynamically similar. And there's a lot that you can do just thinking about this dimensionless number, even though it's usually you can't analytically solve the Navier-Stokes equations and you have to use computation. So looking at this Reynolds number, you can divide the world into low Reynolds numbers less than 1 at the micro scale and high Reynolds number greater than 1 that's inertia dominated at the macro scale. And you see that organisms swim and fly differently. So at low Reynolds numbers, again, viscosity dominates. And you can think of unicellular organisms, bacteria, paramecium. They swim with flagella and cilia. At the higher scale, you'll see birds and whales. They have flapping fins, flapping wings. This is an inertial dominated flow. I'll show you here in a minute that if you try to swim with flapping wings and fins at low Reynolds numbers, it doesn't work. So if you look at a microscope, you don't see things swimming around that look like fish. And this is due to this Reynolds number effect. Now, something else that's interesting is what happens in between when both inertia and viscosity matters. And we'll look at a couple of examples of this today. But in this range, which is typically at the mesoscale, so millimeter scale, you see organisms that have, this is an insect with bristly wings, a copepod with bristly fins. You see a lot of these bristly structures, and I'll talk more about that later. You can also think about internal flows. So high Reynolds number would be the adult heart, trachea, arteries, again, inertia dominated. At the small scale, capillaries, alveolar sacs, viscous dominated, and everything in between. So I've also studied the embryonic heart, and the interesting thing about that is that it starts out as a viscous dominated microscale structure about the width of a human hair, and it grows into something the size of your fist that is inertial dominated, and there are all kinds of changes in between that happen. So this is just an example from the National Committee for Fluid Dynamic Films, where something with a flapping fin is put into glycerin. So it's very low Reynolds number. And it does not swim forward. If you put it in water so that you're at a higher Reynolds number, it does swim forward. And this demonstrates that if you use a reciprocal motion, such as flapping back and forth, in a viscous dominated flow, you don't get much net propulsion. So this has huge consequences, again, for organisms swimming and also for pumping. And this is just one demonstration of what's called reversibility, which is responsible for this effect. So here is an old experiment where the outside of this is turned, the inside cylinder stays stationary, and this is at a higher Reynolds number, so we're going to spin it the outside counterclockwise, stop. We've distorted the dye that was injected. We see some movement continue after we stop, so that's the inertia. And when you rotate the outside back to where you started, everything is distorted. Okay, and this might be what you would expect if you move something in the water, if you're using your hand and going with a reciprocal back and forth type motion, you're going to mix the fluid. Now here at the lower Reynolds number, we're going to do the same thing. So we turn the outside of our cylinder, we're going to turn it back. And because these flows are reversible, we're going to end up exactly where we started. Okay, and you can see the letters RE less than 1 are starting to appear again. And just like the flapping robot, so you can propel yourself forward by flapping in one direction, but then when you move the fin backwards, you get pulled back exactly where you started. And so in this sense, the reversibility of these viscous dominated flows that we typically see at the microscale don't permit net movement. Okay, so as a PhD student, one of the things that I was very interested in after learning about the Reynolds number is what happens at a Reynolds number of 1. Now, mathematically, this is a much harder problem because if we're at very low Reynolds numbers, we can neglect the nonlinear terms, the inertial terms from the equation. And we end up with the Stokes equations that are linear and much easier to deal with. Now, if we are at high Reynolds number, we can neglect viscosity, and we can use some tricks with complex analysis to look at inviscid flows. But at Reynolds number 1, we have the entire Navier-Stokes equations to deal with, and we have to move into very large computations. although there are some things that you can do, back of the envelope approximations. But one of the methods that was developed actually from my advisor at NYU is called the immersed boundary method. And it's been applied to a whole variety of problems in biological fluid dynamics. And there are quite a few important problems where we are in this intermediate Reynolds number regime, where we have to think both about viscosity and inertia. We're dealing with the full nonlinear Navier-Stokes equations. And in addition to that, we have an immersed boundary that is flexible. And so what we would like to do is to think about the full fluid structure interaction. And let's see. So I'm going to go through the immersed boundary method, sort of an overview here in a moment. But the components of this are quite complicated, particularly if you're in 3D. So you have Navier-Stokes solvers. There are a lot of them that are out there. And again, you're solving the Navier-Stokes equations that I showed earlier. But now you have this flexible immersed boundary that's interacting with the fluid. So the immersed boundary method offers a way to deal with this coupling. So you can imagine over here where we look at our immersed structure, we have some elasticity equations that are describing the boundary. And also we need some way to construct this boundary, perhaps using mesh generation softwares. We could also integrate some features of the biology, like muscle mechanics, biochemistry, and so forth, just like we saw earlier with the formation of the blood clot. So the connection between the two is as this boundary is moving and deforming, it is applying a force to the fluid. And then the boundary moves at the local fluid velocity due to what is known as the no-slip condition. Okay, so we have all these components that we need to integrate together. And so, definitely at this point, there are a number of ways to solve fully coupled fluid structure interaction problems. The immersed boundary method from Charlie Peskin was developed in the 70s. It's still used a lot today, just given that it's robust and relatively easy to code up. So I don't mean easy to code, but relative to other things, easy. And the idea behind it is that, let's say we have this box of fluid, and we can discretize the Navier-Stokes equations in Eulerian form on a Cartesian grid. And on this grid, we solve for velocity, pressure, and we have an applied force, again, coming from this boundary. Then we have another grid where we discretize elasticity equations in Lagrangian form on a curvilinear mesh. And here we're solving for the position of that boundary and the force, the elastic force that we then apply to the fluid. And the challenge is that these two grids don't necessarily align. And so how do we transfer information back and forth? Now, there are grid fitting methods that are very powerful. But again, the challenge is if you have a structure that is really deforming in significant ways, you may have to regrid at each time step, which is a huge challenge and introduces a lot of potential failures. So regridding complex structures in 3D is a very challenging problem. Okay, so this is the mathematical formulation of the immersed boundary method. So here we have our Navier-Stokes equations, and here we have our interaction equations, which are integral transforms with delta function kernels. And Lagrangian coordinates are denoted with capital letters and Eulerian with lowercase. And so the main thing is here at this step, capital F is the elastic force on our immersed boundary. And so somehow we have to get that, from the elastic boundary and apply it to our fluid. Okay, so that is done again with this integral transform, and then our boundary has to move at the local fluid velocity, and that's done with analogous integral transform. So why these problems computationally are challenging is that at each time step you have to solve the Navier-Stokes equations with an elastic body force density that you've gotten from solving elasticity equations. You need to then move the boundary at the local fluid velocity that you just solved for, and determine that velocity at each Lagrangian point through interpolation. Then you need to solve the forces exerted on the fluid by the boundary by looking at the elastic deformation of the boundary. And then you have to spread the force from the elastic boundary to the Eulerian grid and use that elastic body force density for the next step. And the challenge is that in immersed boundary simulations that are being applied to biological problems, this might be a 512 cubed spatial grid where you're solving it for something like 100,000, a million, or more time steps. So once you're in 3D, you typically need to move to parallelized adaptive code that you're using a high-performance computer to solve. Okay, and this is just a little schematic diagram of how these interaction equations are working. So this is the mathematical formulation, and when we discretize it, we end up using a regularized delta function to spread the force that we calculated by looking at the elastic deformation of the boundary. Here, this boundary is resisting bending. So there's a force applied to the fluid in this direction, which would act to straighten out our boundary. That force gets applied to local Cartesian grid points using this regularized delta function. And then similarly, here we have our flow field where we've solved for the velocity at each of these nodes. And to figure out what velocity this grid point, this node on the elastic boundary would move, we basically use our regularized delta function to figure out what the velocity is here. Okay, that's a general idea. It does introduce some error, especially since it has the effect of smearing out the boundary through this regularization. And well, so for some problems, it isn't too much of an issue if you're at lower Reynolds numbers with really viscous boundaries. The fact that you've smeared out the boundary isn't so bad. You do have to refine your grid near the boundary. In other problems, it can be a very big deal where you end up with sort of the wrong solution altogether. So you have to be careful. And in my group, we are always checking our results against experiments, and that's one of the nice ways where the computation and the experiments are used in conjunction. So there are more accurate ways of doing this fully coupled fluid structure interaction. The main challenge, though, is that often these methods are more complicated to code. And because of that, I think in part, we don't have open source software available for doing it in 3D, right? So also, there's been a number of people who have specifically used the immersed boundary method and extended it to consider a lot of different elastic structures. So springs that resist stretching, beams that resist bending, massive points, porous layers, muscle fibers, and target points. So all that is great, but again, just thinking of one of the challenges, in terms of applying other methods to these types of problems once you go to 3D is, again, the availability of that open source software in 3D. So Boyce Griffith, who was a grad student while I was at NYU, did his dissertation making an immersed boundary method with adaptive mesh refinement that was parallelized in 3D. And I think it probably took him about 5 years to get it to a point where he could work on problems. It took another 5 years to get it to the point where someone else who was an expert in the immersed boundary method could use it. And then maybe another 5 to 10 years for people who were working in the area of biological fluid dynamics, but not necessarily immersed boundary people to use it. So that's a huge challenge. And I guess this is my pitch, that people who can take new and exciting methods of doing these sorts of problems and provide code that the community can use would be fabulous. So we also have a 2D code that's available in MATLAB and Python. If you're interested, it's a little bit easier to use than Boyce's fully 3D method. Okay, so let's get to some applications. And as I mentioned before, at the mesoscale, where the Reynolds number is close to 1, where you have balanced inertial and viscous forces, we see lots of bristly, hairy structures. So these insects with bristled wings, plankton, copepods, and other tiny swimmers, barnacles, internally microvilli. In the plant world, you see trichomes on leaves, so these bristly surfaces. And so one question is, why do these types of structures come up again and again at these intermediate Reynolds numbers? And so this is a video that I made quite a few years ago, and let me give you a little bit of explanation here. So this is a flow tank that I made with corn syrup. These are push pens, rows of push pens, in sort of a styrofoam board, and I drew lines of dye. And so what you'll see, because this is low Reynolds number, that the pens really have the effect of stopping the flow. So because the flow is so viscous and we've inserted these pens, there's a lot of viscous resistance to the fluid moving between the pens. And these rows of pens can act like a solid structure where very little flow permeates. So you can also change the height, and you see differences. There is some flow through here. You can change the volume fraction, so how tightly packed the pens are, and you get less flow. And so that's just to give you a little bit of intuition for these problems. Now, there was a theoretical analysis from Cheer and Cole using Osine's approximation to look at how much flow is between two cylinders as a function of their spacing, how far apart they are, and the Reynolds number. So they define something called the leakiness, which is the volumetric flow rate that you measure or calculate over, if we had a totally inviscid fluid that could freely move between the cylinders, what that volumetric flow rate is. So if the leakiness is 0, there's no flow between the cylinders. If it's 1, then flow is freely moving between cylinders, but typically it's something in between. And so you can imagine that there could be these transitions where rows of cylinders could act like a solid plate with very little flow between them. And if you change something about the situation, like the Reynolds number, they could act like a leaky break. So here the different lines show different Reynolds numbers. These are based on the diameter of the bristle. The spacing is how many diameters are between the cylinders. So here this would have 10 diameters between each cylinder, so pretty sparsely spaced, 20, 30, 40, and so on. And we see these highly nonlinear transitions where if I'm here and I slightly change my Reynolds number, then I can go from being, functionally a solid paddle to a very leaky one. Also, if I change the spacing, the same thing can happen, going from here to here. So it turns out that organisms use this all the time in a ton of different contexts. And a lot of those examples that I showed you, organisms are taking advantage of these transitions. So I'm going to tell you a bit about what happens with sea fans as one example of this. And so some of the questions we ask when looking at sea fans is how the morphology affects the flow velocity through the sea fan. What are the relative contributions of the Reynolds number and the gap to diameter ratio, so that spacing on the flow? And the significance is that proper flow brings in new food, it removes waste, and allows for efficient food capture. And also these sea fans have to deal with continuous hurricanes, particularly in the Caribbean where they thrive. So it's a challenging mathematical problem because we have many different scales of organization. Here is a group of sea fans. They can be a meter to a couple meters across. But then at the smaller scale, these polyps are the size of about a millimeter. And if you zoom in even more, they have these bristles that are at the scale of tens of microns. Here we've done some flow visualization, just looking at how the flow is seeping between the branches, which it does. But we wanted to quantify that. So we started this project during COVID, where I was doing undergrad research with biology and mathematics students, and we were hoping to go to the Keys to take measurements in the ocean. We weren't able to do that at the time. We have since done it, but we decided that what we really needed to do was to quantify all these different scales and look at what the approximate Reynolds number would be, what's the gap to diameter ratio, and so on. So we picked a couple of different types. These are all sea fans. They have a lot of different forms. We looked at the candelabra form and the reticulate form. And at the larger scale branch level, we measured the diameter and the gap. And then if you zoom into the polyp, we measured the tentacle width to the gap between tentacles. And these little bristles are called pinnules. So we also measured the pinnule diameter to the gap between the pinnules. So 3 scales of organization. And we found pictures on the web and looked at a number of species. This is showing some results at the branch level. So we have the diameter, the gap, and the gap to diameter, and it ranges from about 1 to 4. And again, that depends on the species. So then we decided, well, we have to see how these different gaps to diameters change our flow. And we did that with 2 different types of models. So the first one, we just made a cylinder with periodic boundary conditions. So that would result in, so here's one cylinder, periodic boundary conditions, that would give us an infinite row of cylinders. And we used, in this case, COMSOL to simulate the flow between these cylinders. And we measured the leakiness as a function of the Reynolds number and the gap to diameter ratio. Now, of course, C-fans aren't quite rows of perfect cylinders. So we looked at a couple 3D models that we could find online. It was too difficult to simulate the entire C-fan, so we just took a chunk of it and then simulated it. And this is what we found. So here is our leakiness, similar to the Cheering coal versus gap to diameter for a range of relevant values for the C-fan. The Reynolds number, the changes correspond to changes in velocity. So at these higher Reynolds numbers, this would be in the ocean during very strong flows. And so once you're up this high, the C-fan is basically acting like a leaky paddle or a leaky solid. And this really helps reduce the drag. So if you go to the Keys or the Cayman Islands, you'll see these C-fans everywhere, and they're these huge structures, and they survive all the hurricanes that go through. I mean, some of them don't survive, but a lot of them do. And part of this is, once you have strong flows, the structure is acting like a leaky surface, and the flow moves through it. But the structure also needs to slow down the flow so that this polyps can capture plankton. So in a nice calm day, when the C-fan is feeding and all the polyps are out, we're down in this range where the flow is being slowed. So to capture plankton, the polyps use nematocysts. They have to harpoon the plankton. It might get stuck in a mucus layer and then fed upon, but it's not instantaneous. So having some slower flow helps. Now down at the tentacle level, so this was the branch level, the tentacle level, we're somewhere in this transition zone as well. Down at the level of the pinnules, it's basically just acting like a solid structure. Okay, so multiple levels of organization and interesting things that we can find from that. Now, those results were from our cylinders with periodic boundary conditions. So does this hold for, a more complex structure? And so we looked at the flow in a couple of these holes and measured at different Reynolds numbers how leaky each of the holes were. We knew the Reynolds number and we could estimate, a gap to diameter ratio. It's a little bit crude, but here is our leakiness graph for Reynolds numbers at the 3 different holes we considered and our estimate for what the gap to diameter ratio was. And we were pretty close to the cylinder simulations, maybe 10% off, but still close enough that, we can say that this whole structure is also going to be in that intermediate regime. Now, I think in the interest of time, I won't talk too much about this, but we are developing a what we're calling a planktos package where we can simulate little plankton, brine shrimp, and copepods that move around with some different rules. Maybe they can sense a predator and try to escape. In this case, they're just moving with Brownian motion. And they're moving through a complex 3D structure that they interact with, and maybe they're captured. So that framework is available on GitHub. And it's been developed in part working with all of these folks. And so I'm not going to say too much about that. other than we still have some work to do, but we are getting interesting results on that. And we've looked also at the addition of polyps. So all the studies I showed you before, we were just looking at the branch level. We didn't have these polyps sticking out from the structure, which is what happens when they feed. Now, during a hurricane or strong flows, the polyps contract. So that probably is a good model for, what's going on in stronger flows. But the polyps have the effect of slowing the flow even more, as you could imagine. Instead of just having this branch, now you have one with all these structures sticking out. And here's just a comparison where we're looking at the leakiness over the polyps. So what is happening where the tentacles are, and that is slower. That would be this line. Between the polyps, it actually speeds up. And then this is just a cylinder with no polyps. Okay, so one more quick example. This is looking at a related group of pulsing soft corals. So over here on the right, you can see these corals. They're in the Xenia family. And they pulse most of the day and evening. They have 8 tentacles with muscles within the tentacles. And it's thought that the currents that they produce can enhance photosynthesis of their symbionts by up to an order of magnitude. So they're doing this to increase the photosynthetic process by removing oxygen, basically. So in photosynthesis, oxygen is a waste product. And they're at a lower Reynolds number, maybe around 10. And without the pulsing, oxygen is a waste product. It would diffuse away from the corals and hang out near all the polyps and slow the rate of photosynthesis if the polyps weren't pulsing. And then presumably the polyps get enough benefit out of this that it makes, the energy spent constantly pulsing worthwhile. So this is what it looks like. This is some field work done with my student and collaborators in Israel. And what you can see is that each polyp is forming a small jet. And fluid is recirculating above the tentacles and within, and then being pushed away. And we've had a number of questions about this, like, are the pulses coordinated? What is the flow features that are produced? How does pulsing mix the fluid to enhance gas exchange? So these are experimental results using particle image velocimetry just to quantify the jets that are formed by each of these polyps. And one thing to note is that there is a continuous upward jet above each of the polyps. And during each pulse, during the expansion phase, fluid is brought in between the tentacles, and then that volume of fluid is pushed away and up into the water column. So here is one of our numerical simulations, one of our earliest ones of the flow that's being produced by these polyps. And we didn't quite get it right, so you might see that there is not a strong upward jet that is always present here. You see it during the contraction, but during the expansion, it goes away. So we still had some more work to do in that case. We did some comparison on the right, or the immersed boundary simulations on the left, or the measurements from the coral. We measured at different distances from the coral. And the thing to notice here, so here's the 0 line. This is the average vertical velocity in the real coral, and it's always above 1 millimeter a second. So during the contraction, you get this spike, but it is always consistently positive in the upward direction. And in our simulations, it plummets to 0. So we get this spike when it contracts, and then it falls to 0, and then another spike. So somehow we weren't capturing this feature, and it made us go back and think a little bit more about the model and what we were getting wrong. You could do a few other things varying the Reynolds number. I think the main thing that I want to show you here is that at 0.5, we really see the reversibility. So there's a jet upwards, and then it's pulled back down. So it's pushed up and pulled back down. So you won't see something pulsing with this reciprocal motion at low Reynolds numbers. Once you get up to higher Reynolds numbers, you do start to see a jet. And this is the Reynolds number where the animals live, at around 10. So I'm just going to end with one of our newer models where we try to incorporate some of the biology. And in this case, so the coral polyp here is modeled as an elastic neo-Hookean material. And then the colors are showing you where an active tension is applied to the material to represent the effect of the muscles. And there are different ways you could do it. Here we have sort of a strong muscle effect of the muscles going out to the tips. And here it's stronger near the base and then tapers off quickly. There are a lot of design choices that you have to make when constructing these types of models. And so in order to get the thing to pulse, we apply the tension during the contraction phase. So that's each of these spikes. And then we remove it during the expansion phase. So just like the real animal, there's an applied tension, the tentacles contract, it's removed, and they expand due to the passive elastic properties of the tentacles. So here is the real polyp on the right. Here are newer models on the left. And if we have both a variable stiffness and sort of that tapered muscular structure, we are starting to see a stronger jet. And I think the take-home message here is that when we start to incorporate more of the biology into our simulations, we see more realistic results. And I think it's interesting to see that the placement of the muscle, how the activation isn't uniform, how all these things can really affect the flow fields that are generated. And we really have this nice coupled problem. Okay. So I think in the interest of time, I will end there, but I do want to take a moment to say that the great thing about this work is that I have collaborated with all kinds of people on engineering, mathematics, biology, oceanography, physics, and have been funded from different divisions of NSF and the Burroughs Wellcome Fund to do this. So I'll stop there and happy to take any questions.
Thank you very much, Professor Miller. Thank you very much for your impressive and beautiful talk. There are the most beautiful simulations that I have ever seen. And it's really nice that, yeah, it's really impressive, the color. Yeah, I can imagine the work that you have done there. Also, it's really nice and impressive that you do a field work. So you have this impressive work. It's really impressive, these bridges between biology and mathematics. And yeah, it's amazing.
Well, thank you. Yeah, and I should say that a lot of the videos were worked on quite extensively by Alex Hoover and Mateo Santiago, who Alex was my grad student and Mateo was my postdoc. And I think one of the nice things is that they are both very artistic.
Mm-hmm.
And they have spent a lot of time just making how can you communicate information and make these visuals compelling. So want to be sure to give props to them for that.
They are amazing. Yeah. Thank you very much. Does anyone have any questions? Yes, Torben, please.
Yes, so I first of all want to agree with Andrea. I also find it very much impressive, all the videos you have shown. My question is concerning the analytical tools you may be interested in and you use in your work.
Oh, yeah. So, there are, in terms of analytical tools, so you can do some things when you look at Oseen's approximation, using asymptotics to get some, especially with the leakiness chart that I showed. So this, well, let's see. My computer is a little bit unhappy. Yeah, so all of this was done by using Oseen's approximation to the Navier-Stokes equations, which is, I think amazing that you're able to get this much detail at these intermediate Reynolds numbers, and they match the simulations and experiments just super well. One thing that I'm working on with one of my old students is to come up with a method of regularized Oseen-Lutz. So there's an analytical solution for what the flow field is like around a point force using Oseen's approximation. And since it's linear, then you can just sum everything up and get the flow field due to a whole array of these point forces. And it's computationally much more efficient than solving Navier-Stokes equations. So this has been done with Stokes-Lutz. So method of regularized Stokes-Lutz from Ricardo Cortez has been amazing and used at the microscale for a whole range of biological problems. So this is based, similar to that method, but we don't have it done yet. So hopefully in a couple of years, and then once we have it, we'll be sharing the code with the community as well.
Okay, thank you. Thanks.
Thank you very much for your question, Torben. Does anyone have any questions? Okay, I would like to ask you something, Professor Miller. How can these fluid dynamics or computational mathematical models can be used to predict and simulate these effects of different climate change scenarios on the ecology of these coral reefs?
Yeah, so, I think climate change has a few different effects. So one of them being that you have more frequent and stronger hurricanes. And so the sea fans, one thing that I noticed about them is that a hurricane would come through in the Keys, and a lot of the hard coral would be broken and devastated from this. But the sea fans would really proliferate. I think one thing is that they're faster growing, but somehow they're also, better adapted to withstand these really strong and frequent hurricanes, just in terms of drag reduction. Another thing, so there's ocean acidification and then warming. The soft corals are doing better in general than the hard corals from both. But in Florida, in the Keys, last summer and this summer had been so warm that almost everything is bleaching. So almost all of the corals have these symbiotes that photosynthesize. And when bleaching happens, the symbiotes leave. So either they're kicked out by the coral or they leave. And then after bleaching, the corals typically die. So after some of the warmer events, last year in the Keys, lots of things bleached and died. I think the hard corals are more sensitive to this, but a few of the things in terms of morphology, if you have more flow going through, it's probably better because at the very top layer of the ocean, could get really, really warm. So when we were diving, I would say the first 10 feet felt like a hot tub last year when we were in the Keys. And so any coral that's in more shallow regions with less flow during the day is just going to heat up. And then that's probably going to cause bleaching. So thinking of the corals that are maybe spaced further apart that have more flow going through, they're going to be a bit more resistant to this, but at some point it's not going to matter. So I know going to the Keys the past few years has been pretty depressing. There is a lot of effort trying to find corals, genetic strains that are more adapted to heat. And there's some progress being made there. I don't think that we know, the mechanism why some strains are performing better than others, but that could be a cool thing to look at mathematically. So we have these genotypes, but what are the morphological and phenotypic features that make them able to withstand more? So.
Oh, okay, interesting. And really, it's really sad. Duban, it's raising his hand. You can.
Okay, thank you. No, Professor Miller, thank you for the very inspiring talk. I just have a question because, I am also looking to do my research in this very applied setting that you chose, which is, of course, very interesting. I am more from the side of harmonic analysis. And for us, let's say the analysis of Navier stocks is very complex, right? Even if one neglect, let's say, viscosity effect, then one fall in the model of Euler equations. Just my question is if this simplified model, if that simplified model have you also considered in your setting, and if you gain something when you consider this kind of simplified model, right?
Oh yeah, yeah. So I definitely think that all approaches have different things to offer that really complement each other. So with our simulations, we're very constrained. We can look at one polyp, maybe two or three. And the good thing about it is that it's a high fidelity model. We get a lot of details about flow fields close to the polyp, but you could then ask, there are thousands, tens, hundreds of thousands of polyps. And what is the net effect of all of them? And we can't answer that using these type of tools. But you can, once you zoom out to that scale, you can imagine using Euler equations and having, constructing point vortices that would make some sort of jet. And then trying to understand each of those little jets could be a polyp, and then with different arrangements, how is that going to affect the larger scale flow? And then if you think going down to the smaller scale and just focusing on, let's say the cilia, which are in the viscous dominated regime. So you can use, Stokes equations and consider the flow fields that are generated by the cilia. So I think one nice thing is that there's room for all different sorts of approaches and that they all really complement each other. They have different things to offer.
Thank you very much.
Thank you very much, Professor Miller. Happy Thanksgiving again.
Thank you. Thanks for the invitation.
No, we are really honored to have you here. Thank you very much. For the next session, I am delighted to pass the sharing duties to Karina Navarro, who will guide us through the upcoming presentation.
Yes, thank you, Andrea. Okay, it's with great pleasure that I introduce the Professor Thais Jordão. Thais Jordão is a distinguished Brazilian mathematician and associated professor in the Department of Mathematics at the Institute of Mathematical and Computer Science, ICMC, at the University of São Paulo, São Carlos. Within the scope of research, he works on the following topics: approximation theory, Fourier analysis, analysis on the sphere, and operator theory in integrals. Thais earned her doctorate in mathematics from the University of São Paulo in 2012. Following this, she held postdoctoral positions at Mathematical Research Center, CRM, Spain, Institute of Mathematical and Computer Science, Universidad of São Paulo, ICMC, Brazil, and Missouri State University, MSU, United States. Today, she will talk about an asymptotic analysis of entropy numbers of reproducing Hilbert spaces of zonal kernels. And she, as a female mathematician, she will share with us how she perceived the challenge faced by women in the community when trying to make their way in the academic field. Please, Professor Thais, you can start.
Oh, hi.
Hello.
So the answer, I should give the answer, right?
Yes.
Okay,
please.
I will read it, okay? All right. My answer was that the lack of women and nominations of women in leadership positions who recognize and encourage the talent of the others, as happens within male professional communities, is evident. For this, community committed to raising awareness and, most importantly, to addressing gender disparities in academia is necessary. It's already known that non-academic institutions perform better under female leadership compared to the male leadership. This same should hold true in academia. We all know examples of female leaders who, despite the challenges of having their work consistently judged more harshly and needing to work at least twice as hard as men in general to achieve the same professional recognition, have excellent with charisma, collaboration, communication, and democratic leadership in their roles. We had the opportunity to witness their work, which consistently outperformed expectations. So now I need my presentation, right? And I need to give some authorization.
You are co-host now. Let me check. Yes, you are co-host. Okay.
Yeah. Mm-hmm.
Perfect. Okay.
Can you see my slides?
We can.
All right. Can I start?
Please.
Thank you, Karina, for the presentation. I'm sorry about the question. I was a little bit surprised because I thought you guys would read the question. Fortunately, I was with the message here, so I could read it. So good evening. I would like to thank all those present for participating in this event and for attending this lecture. It's a huge pleasure to be here with today to share a little bit of my research. And I also would like to extend my gratitude to the organizing committee, especially Karina, Andrea, and Milton, for their invitation, their careful organization of the event, and their initiative to promote through this ISAAC-ICMAM Conference of Women in Mathematics, the dissemination and also the inclusion of Latin America within the intercontinental framework, especially with respect to the mathematics developed by female researchers. So my challenge for myself for this lecture was to prepare something that would convince you that the results and concepts I will present here are both fascinating and have some practical applications. But I will not extend myself through the technical details, but I will deliver some idea of the main tools and technique employed in the results. I will also present some extension of the results that I will present, and mainly I would like to explain a little bit my title here. Asymptotic analysis of entropy numbers means to find somehow upper and lower bounds for a quantity called entropy numbers. I would like to also warn to those who are familiar with the concept of entropy numbers that in this talk, I will not refer to the numbers directly from the definition of coming from the ergodic theory, but instead they are related to the number of balls as a kind of topological definition here. It's a number. This is a number of balls we need to cover some subset in a metric space. And so this is the kind of thing I want to study. And the framework, the basic framework is defined by the rest of the title. Reproducing Hilbert spaces of zonal kernels. Reproducing Hilbert spaces are special classes of functions spaces. These are in general separable Hilbert spaces, very nice for applications. And from a mathematical point of view, they are nice spaces because we have very good, I could say, properties on this space. I'll show you. So the main references here are the number 1. The reference 1, there are some results coming from the PhD thesis of Karina Gonzalez, one of the organizers. It was my pleasure to advise this thesis. And the extension of this result, most of these results, some improvements of them were obtained last first half of the year, and they are submitted for publication. Okay, The motivation for the study of these numbers, called covariant numbers, which we can find defined in the Wikipedia as the number of balls of given size, given radius needed to cover a given space. Here's a subspace in a metric space. It's kind of a simple concept. Of course, it's related with the concept of capacity or some kind of trying of measure the capacity of subsets in metric spaces. But the important thing about these numbers is given by the machine learning theory, basically. In particular, the zonal kernels, these kernels are functions in two variable spaces that are invariant under rotation in both variables. This special class of functions in two variables play an important role in the mathematical foundation of the methods, including machine learning or in algorithms employing kernel-based methods. Okay, but recently, I'd like to use this paper, the foundations on the mathematical foundations of learning, because the main idea comes from this paper from 2002, but recently in a very nice book published in 2018, for non-specialists in machine learning, as I am, we can find some nice idea why this is important in the big data era. So the basic idea is that the inner product in a Hilbert space can be replaced by the concept of positive definite kernels. And this extension is very nice. This carries a lot of nice properties that the inner product itself has on the subset, and more important than that is that the algorithms use this kind of functions. So in mathematics, the idea basically is given in this slide. What we want is, in the end of the slide, we can find the error function. The main idea of the problem here will be to estimate probabilistically this error in the end of the slide. But initially, what we have here is x times y with a distribution measure on that. X usually is a subset of some Euclidean space, also usually compact or bounded, and y is the complex or the real numbers. H here is called hypothesis spaces, and also this is a subset of the continuous functions defined on X. With these tools, we can define the generalization error of F in the hypothesis spaces. This is given by this integral. We can also define the empirical error of a sample in the X times Y space. This is given by this average of squares. And finally, we can define the error of a function in the hypothesis spaces by this quantity here. And this quantity is basically the difference, the error of F defined here, the generalization error, minus the generalization error in the minimum of the functions that minimize. This is a minimizer of the generalization error. So the main problem here is to minimize this error function in very nice hypothesis spaces, and all this construction here depends on the setting, depends on the application, depends on the algorithm that we want to apply. But with this in hand, the main result about the upper estimates for the probabilistic error we can have using this method is given by this formula. So it's not beautiful, but it's very nice, because here we can find that the probability under the samples of the error analyzed in the mean to be less than equal epsilon. This is bigger than 1 minus C. This number is the covariant number, something I'm going to define with you, but this is the main subject of the talk. So I put this in the slide just as a form to inspire why we justify why we want to study this number. So this illustrates very well the necessity to find boundaries, to do analysis of these sort of numbers. But not less important than that, we can find in this very nice book authored by Peach, The History of Banach Spaces and Linear Operators, that the entropy numbers, or S numbers, a class of approximation numbers where the covariant numbers also can be placed into, or all the eigenvalues of operators. They are also related concepts. Other subjects are in the considered more the modern Banach space theory. So they are recently developed subjects. Most of them are going to complete 40 years, as I am, in 2025. So we have a lot of work to do on these subjects yet. And also we can see here in the section 6.8, there are a lot of applications in probability theory on Banach spaces. Okay, so I will present you the basic setting here. I work on the sphere, the dimensional sphere, in the D+1 Euclidean space. So this is called the spherical setting. For me, here the dimension is bigger than 2. And for me, L2 of the sphere is the regular Hilbert spaces of the mensurable functions defined on the sphere to real numbers with the induced Lebesgue measure from the Euclidean space as a manifold. So the square integrable functions, we can endow the space with this inner product. And it's well known that this space has the spherical harmonics as subspaces of this is a space of polynomials, harmonious polynomials of degree k in the +1 variable. I'm going to denote the basis of each one of these spaces by Skj. Here, for me, also PKD is the Legendre polynomial of degree k. The Legendre polynomial is related with the spherical harmonics by this called addition formula. And they can be seen as the eigenfunctions, the radial part, the eigenfunctions of the radial part of the Laplace Beltrami operator on the sphere. Okay, so these are the basic notation. Here, I forgot to mention, this tau is kind of important in our estimation, is the dimension of each of the spherical harmonics. Okay, so with this in hand, for any function in any square integral function, we can associate a Fourier series given terms of this harmonical spherical. They are a complete system of orthonormal functions here in L2. This structure, I'm sorry. So we keep this in mind and go to the concept of kernel. Kernel is just a function of two variables defined on the one set times the same set to real or complex values. Here I work on the real. So I call by isotropic or zonal kernel the function that satisfies this equality for some continuous functions defined on -1, 1. This is the same thing I said in the beginning on the sphere. For continuous functions satisfying this equality, this is equivalent to the fact that the kernel is invariant under rotations, fixing the pole of the sphere. And for positive definite kernels, we want to mean just a kernel satisfying this inequality, the quadratic form associated for any natural number is always non-negative. This definition with these two concepts, a zonal kernel and this positive definite kernel, we have available the College-Schoenberg characterization for zonal kernels. This is a spherical version of the Bochner's theorem, and it says that the kernel can be written as a series in terms of the Legendre polynomial of this form, where the sequence of real numbers appear here, called Schoenberg coefficients, form a sequence in L1. They are a summable sequence of real numbers. So this is a very nice characterization for zonal continuous and positive definite kernels. And we, Karina, mainly used these characterizations for the kernel, inspired by the previous example that she had studied. Okay, so if we apply the addition formula relating the Legendre polynomial with the spherical harmonics, we have this another representation for the zonal positive definite kernel. Okay. And associated to a positive definite kernel, here's the main concept that machine learning and borrows from the mathematics, is the reproducing kernel Hilbert spaces. Associated to a positive definite kernel, there is a very famous theorem that says that there exists just one Hilbert space associated. And then these Hilbert spaces is usually used as hypothesis spaces in the first slide I present to you. So A Hilbert space, reproducing Hilbert space, is just a Hilbert space that contains all the functions of this form. So we fix one of the variables of the function, and then we have a function defined on the sphere. This function must be in the Hilbert space. Also, the span of this kind of function must be dense in the space. And the reproducing property says that the function has its value in of his value reproduced by the inner product of the space, like this. This is a very nice property because from this we can, all the properties that the kernel has, we can carry somehow for the functions in the spaces. So if the kernel is a continuous function, just Cauchy-Schwarz inequality ensures that the Hilbert space can be embedded in the space of continuous functions defined on the sphere. So this is enough to have hypothesis space. And the interest here is in the covering numbers of this embedding. As I said, the covering number is a concept defined on metric spaces. And here it is formally a subset of a metric space. We have here a epsilon positive, then the notation C epsilon A is the covering number, and this is defined as the minimal numbers of ball we need to cover A with the radius epsilon. For an operator, since we have an operator, the embedding operator from the Hilbert space to the continuous space of functions defined on the sphere, the covering numbers of an operator are defined in terms of the covering numbers of the subsets of metric spaces, just looking at the image of the unit ball by the operator. In our case, it's just the embedding. So we just need to look at the image in the space of continuous functions of the covering numbers. This is what I'm going to show you. For that, we consider the basic setting is a zonal positive definite kernel. And since the Schoenberg, the characterizations of Schoenberg is available, we write the kernel this way, and we call AK the Schoenberg sequence of the kernel. It's kind of a nice kernel because this is invariant under rotation, a continuous kernel, positive definite kernel. It seems a lot for a kernel, but it's not necessarily is. For most of them applying the result, this presents a very general setting. So basically what Karina found out on the sphere was that if we have the framework of the previous slide and the coefficients of the kernel are between two geometric sequences, one with delta and another with theta, then we can find upper and lower estimates for the covering numbers. So here we can see this limit inf, we have the logarithm of the covering number of the embedding over the Ln function, and here we have the dimension of the Euclidean space where the sphere is. And for the upper bound, we also have the logarithm of the number, the same function here, and this constant depending also on the dimension of this sphere. So this is super new because before this theorem, some estimate like this presenting on the constants included in the process of finding bounds for the covering number were available just for the Gaussian kernel. So we had just one example of kernel with such a nice estimates. So this is the first theorem. And this delivers us the already known what we call the weak equivalence for the covering numbers of this embedding. So the logarithm of this behaves weakly as the logarithm of 1 over epsilon to a power of the dimension of the Euclidean spaces. Okay. How is the proof? How we can get nice estimates, lower and upper bounds? We basically have nice theory developed for these numbers. So we just apply them, trying to minimize the efforts and also to find the right way to fit into the hypothesis of the results we need to apply. For that, we need to consider the orthogonal complete system for the Hilbert spaces associated to our kernel. This is not a difficult thing to do because it's well known that they are just a kind of new normalization of the basis of the square integrable spaces, the Lebesgue square integrable spaces. So we know that collecting all of this new normalization of the spherical harmonics, we have a basis for the Hilbert spaces. We are going to denote P index M, the orthogonal projection in the first VM spaces. VM spaces is the collection of all the first spaces until K. K is the degree to M, 1 to M, 0 to M. And the orthogonal complement of that we call of PMS. So it's kind of easy because these are just orthogonal projections in Hilbert spaces. Okay, so we can write any function in the reproducing Hilbert space using these projections, like I showed in blue. And using this information, we have some properties of the covering numbers. If we have an operator written as a sum of another two operators, then we can upper estimate this number by the product of the covering numbers of one operator and another operator. Which is nice because this operator here, the complement of the orthogonal projection, we can make this operator with a very small norm. The operator norm is very small, and we can make this number, we can disappear with this number here, just change the quantity by 1, because then we can cover this this thing with just one ball. And these are just general properties of the cover number. As I said, most of them can be found at this reference in the footnote from Ninetz. Okay. Then, using this information, as I said, from the hypothesis we have on the coefficients of the kernel, we very trickily can do this construction for any positive epsilon. we consider a positive integer number satisfying this inequality. So this kind of discretization, I would say, of the positive real numbers is nice because then we can transform the cover number related to the orthogonal projection of the rest as 1, and then we gain this basic upper estimate for the original cover number, and this estimate is based on the operator norm of the finite dimensional projection, and here the dimension of the space, the domain of this projection. So contra domain of this projection. So here we have now a lot of work to do, a lot of calculations, because this operator norm is not hard to compute. This dimension is not hard also to compute, but this quantity can be a little bit tough to handle. But Karina made it wonderfully, and we get that we can upper estimate the logarithm of the cover number by this quantity in the right side hand of the inequality. We need to apply this strong equivalence. This means that at infinity, the quotient of the quantities goes to 1. This is well known from the dimension of the harmonical spherical spaces. And also, as I said, the operator norm of the projections super easy to compute, and it's just the summation of the first n plus 1 coefficients of the kernel. So this is enough for the upper estimate. For the lower estimate, we have this another basic property for the covering numbers. If we have an operator between two Euclidean spaces, then we have an upper bound given by the square root of the adjoint with the operator t here. So we just need, in our case, to construct a very nice operator from two n-dimensional Hilbert spaces. So we are going to use the finite dimensional projections and do a lot of calculations again. So this is the basic chain. It's used to produce the operator T we want. It's a kind of long sequence, but it's not hard because they are just embeddings. And also it's not hard to find out that the depth of this thing, or where Tm are basically the embeddings of the previous slides, are this product. And here we have the coefficients of the kernel. Here we have the dimension of the spherical harmonic spaces, and also here in the power. So it's a little bit hard to compute this, to estimate this, but it's also possible. And then doing a little bit of that, we can gain the estimate I have stated in the theorem. I didn't bring it again. So these were the results on the spherical setting. After that, we noticed that the main idea of getting very nice estimates for the covering numbers were applying the structure we have gained by the harmonic analysis developed on the sphere. And we know a very nice class of manifolds which has well-developed harmonic analysis, which is almost the same thing that the one on the sphere. So we could extend the results on these manifolds, but I will not. I'm not going into the details of these manifolds because they are completely characterized. So a compact two-point homogeneous space here is just a Riemannian manifold. A Riemannian manifold with a normalized metric where all the geodesics have the same length. We can normalize it by having the length 2 pi as on this sphere. So we can consider the volume element on this manifold and also the space of functions, integrable functions on this manifold, very similar as on the sphere. I will skip this slide, but those who are interested on the similarity with the sphere, it comes from the characterization of these manifolds as orbit spaces of compact subgroups of motions on the manifold. And the Haar measure here is related to the measure I just said in the previous slide. This structure, this is geometrical structure of these manifolds are enough to prove that are just 4 classes of these spaces, and I call one example. The example is the elliptic plane. We have just the P16, but the 4 classes here, we have the spheres, the real projective spaces, the complex projective spaces, and then quaternion projective spaces. So all these 4 classes, we can extend the results just considering as on the sphere, the Laplace-Beltrami operator on the manifold. So in each of the classes, we have different parameters dictating here the powers of these polynomials. And then we have the similar construction than we have on the sphere. We have the eigenvalues associated to the Laplace-Beltrami operator. We have the spaces of spherical harmonics defined on these spaces. We also have then the Fourier series expansion for functions on square integral functions on these manifolds. And the concept of zonality of these on these manifolds are very similar to the sphere, and they are given in terms of the rotations, the motions of the manifold. So a zonal or isotropic kernel here is the one which is invariant under motion fixing a pole in the manifold. This is equivalent to say that the kernel can be written in terms of a continuous function defined on the closed interval from 1 to -1, just using the geodesic distance. And this is the same thing, the proof is the same made on the sphere. And originally, we can find this in the Charles Dunkel thesis. This was a student of Houdin. Okay, so on these manifolds, we also have in a result from 2022, the Schoenberg characterization for the kernel. So a zonal PD kernel on the manifold can be written in terms of non-negative coefficients. And here instead of the Legendre polynomial, we have the generalization of these orthogonal polynomials, the Jacobi polynomials. Analogously to the spherical setting, the Jacobi polynomials are the eigenfunctions of the radial part of the Laplace-Beltrami operator on this manifold. Okay, so this is enough. We can also extend now all the results, the upper and the lower estimates on the spherical setting, but adding a lot of obstacles, because here the dimension of the spaces, everything is a lot of more complicated than in the spherical setting. But still this way, we can get upper and lower estimate, just make some assumptions on the coefficients of the kernel, the Schoenberg coefficients. The first assumption to gain an upper estimate is to have a kind of upper estimate in terms of a geometric sequence, and also the lower estimate in terms and possibly another geometric sequence. And again, these coefficients are very sharp, I would say. This is important for applications. We recently find out. That's why we pay so many attention into find nice estimates and also nice coefficients accompanying these estimates. And it's very important to have the dimension of the manifold explicitly in the estimates, because also the problem to find when this limit exists is kind of, it's dependent on the dimension of the manifold. Okay. As a corollary, now we have a weak equivalence for kernels having sequence of coefficients as a geometric sequence. And this weak equivalence says that the logarithm of the covariant number behaves like the d plus 1 power of the logarithm of 1 over epsilon. This is also new on the manifold because, as I said, the more general we have on these results, before that was for the Gaussian kernel on the Euclidean space. So this is a very nice extension of the results on the spherical setting. Okay, here I present you some acknowledgements, the São Paulo Research Foundation, my grant, and at the time Karina was receiving a grant from Yerevan State University Foundation. Thank you.
Okay, thank you very much. I am very happy for you accepting the invitation to give a talk in this special conference of women in mathematics.
I was concerned about the weather because here we kind of have a very strong rain right now, and I was concerned about the power. Yeah.
Oh, nice, great, great. Yeah, so the presentation was very complete, very nice. This topic is obviously very attractive to me. Okay, let me see. Let me check the chat. Maybe we have questions. Does anyone have any questions or comments? Please raise your virtual hand if you have a question, or you can write on the chat also. Okay, let me check. Okay, if not, maybe I will take this opportunity to do one question, just one question, about the properties of the coding number. Because currently I am working with a complex space, and the properties for the coding number are to real space, right? So do you think if we can extend this property to the complex spaces?
Yeah,
Or
but usually we gain two power in the properties. The basic estimates, you know?
Yeah.
The basic estimates, usually we gain I square in both. So instead of here, for example, that on n, we should have 2n.
Okay, nice.
And also the upper estimate, usually. When we talk about cover numbers of subsets, but probably for operators, something similar should hold.
Okay, nice. Thank you. Thank you so much. Thank you so much, Professor Thais, again.
Thank you, Karina.
Okay, for the next session, I am delighted to pass the sharing duties to Andrea Hurtado, who will guide us through the upcoming video. Let me check the time. Okay, are missing 8 minutes, so we will return soon.
See you in 8 minutes.
el corazón de América Latina, nuestros proyectos trascienden fronteras para construir un futuro de descubrimiento, innovación y transformación. Bienvenidos. Nosotros somos ICMAM Latinoamérica, donde las matemáticas abren la puerta hacia un mundo de posibilidades. El estudio profundo de la naturaleza es la fuente más fértil de descubrimientos matemáticos. Los avances matemáticos están intrínsecamente ligados al progreso de la sociedad en todas sus etapas. Las matemáticas sustentan campos tan diversos como la física, la biología, la economía, la tecnología, la arquitectura, entre muchas otras. Es por esto que en ICMAM Latinoamérica nos dedicamos al fomento de su investigación con el fin de seguir acercando todas sus cualidades a nuestra sociedad. Nuestra iniciativa nació en la Universidad del Valle en Cali, Colombia. En 2020 celebramos la primera edición del evento y gracias a sus extraordinarios resultados se sentaron las bases para la edición 2022, el cual se consolidó con un alto impacto internacional. En la actualidad, América Latina enfrenta desafíos en la obtención de recursos, becas e interacción internacional en investigación científica. A pesar de esto, reconocemos el talento matemático en nuestra región y su valor potencial a nivel global. Por esta razón, desde ICMAM estamos comprometidos a superar las barreras que limitan el acceso a entornos académicos de excelencia y hemos comenzado a convertir estos desafíos en oportunidades, estableciendo espacios de interacción y alianza entre centros de investigación matemática a nivel mundial. Con la colaboración de más de 50 expertos internacionales, destacamos el trabajo de jóvenes estudiantes de posgrado, promoviendo sus investigaciones. Los acercamos a congresos y bienales en diferentes países. Creamos espacios virtuales para que los investigadores emergentes interactúen con científicos de renombre, como Terence Tao, Simon Donaldson, Tatiana Toro, Carlos Kenning, Charles Pfefferman, Enrique Suazua y Christine Lauter. Además de esto, prestamos especial importancia en visibilizar y destacar las mujeres de nuestra comunidad científica y matemática en nuestras actividades y alianzas. Reconocemos que solo a través de la colaboración, la unión de conocimientos y la diversidad de perspectivas, podemos superar cualquier desafío que se presente en nuestra sociedad y avanzar en el entendimiento de la naturaleza. Creemos firmemente que la igualdad de género y la inclusión son fundamentales para lograr avances significativos en el mundo de la ciencia y la investigación, y estamos comprometidos en promover estos valores. En ICMAM Latinoamérica, te invitamos a unirte a nosotros en esta travesía donde las matemáticas transforman realidades hacia el descubrimiento, la innovación y la excelencia en la investigación. Juntos podemos construir un mundo que forje un mañana lleno de posibilidades gracias a la matemática y sus aplicaciones. Únete a ICMAM y sé parte de esta inspiradora historia de cambio y progreso.
As we continue with the ISAAC-ICMAM Women in Mathematics Conference, I am honored to introduce a very special video from the International Mathematical Union, IMU, dedicated to celebrating women in mathematics. This video showcases the stories, achievements, and challenges faced by women mathematicians from around the world. It serves as a powerful reminder of the diversity and resilience within our community, as well as the importance of creating spaces like this conference where we can share knowledge, inspire one another, and advocate for equity in the field of mathematics. Through this video, we hope to reflect on the collective progress made, while also recognizing the work still ahead to ensure that every aspiring mathematician has the opportunity to thrive. So let us watch and celebrate the remarkable contributions of women in mathematics. Thank you. Sorry, we will put the video again because we had some problem with the audio. So please wait for just 1 minute. Thank you very much.
The Department of Mathematics, IIT Bombay, is one of the largest mathematics departments in the country, and we have the vision of being the best department. I am the first woman HOD of this department. Right from the beginning, there were so many difficulties and hurdles that I could never plan my career. All I knew that I wanted to be a teacher. I was very passionate about teaching. My supervisor, Professor Bhattacharya, who trained me in the area of finite element methods. I was his first female student. He was more nervous, probably than me trying to start with a PhD degree. He was a strict person, but he had a lot of respect and he appreciated my problems. After 7 months of my joining PhD program, I mentioned that I wanted to get married. A couple of years later, I told him that I'm going to have a baby. Then in between, my mother was diagnosed with a terminal illness and my father died. But I believe that the challenges made me a much stronger person. I got a wonderful set of colleagues who really helped me out in all difficulties and helped me share my responsibilities. There are a lot of international projects and national projects which the supervisor and the student
comes at very early in the department, I'm sure that she will having 100 meetings around. In spite of all those things, she finds time to chat with us, and she's really caring.
Her being the head of the department of mathematics, there's a lot of pressure on her, there's a lot of work she does. I've not met too many people who work so hard in their life, not just the work aspect but the family and home aspect as well. That's what I love most about my mother.
Excellence in Teaching Awards of IIT Bombay has been constituted to recognize the efforts of teachers, and it's based on student evaluation. I have received this award 3 times in my career. The International Math Union, IMU, is doing a great job in helping women network, and I find this is a very good program in encouraging students and building a confidence in them. For women who want to really excel in mathematics, you may find difficulties, you may find problems. So never give up on whatever you want to do and do good research.
De mathématiques aussi aux États-Unis, lui que je voulais atteindre. Je me suis rendu compte que j'étais très bien en mathématiques, pour exemple pour laquelle j'ai fait un bac scientifique et après mon bac, je me suis inscrite en mathématiques. Il faut être très courageuse quand tu es une fille parce que pour fréquenter même à Yaoundé 1, c'était pas évident. Pour avoir une place, il fallait bagarrer pour avoir une place pour faire cours. Donc, et parfois les garçons me demandaient, vous les filles qui font les mathématiques, est-ce que vous allez vous marier un jour? Ils nous décourageaient souvent comme ça. Et ce qui faisait que ça me motivait à leur montrer que moi aussi je peux faire ce que les garçons font. Le titre de ma thèse, c'était la recherche des primitives pour la cryptographie à base de couplage. C'est vraiment axé sur la cryptographie, sur les couplages, qui est une application de l'algèbre. Là où je suis à Marois, je suis la seule mathématicienne de toute l'université. Je suis affectée au département d'informatique et télécommunications. Je suis dans les cours d'algèbre, arithmétique, théorie des nombres. Première année, j'ai près de 350 étudiants. Mais maintenant, quand même avec le temps, plus le temps passe, il y a plus de filles qui font l'effort d'être là. Elles arrivent à avoir une licence en mathématiques. Peut-être continuer, c'est un peu compliqué. C'est pour ça que j'ai eu l'idée de mettre l'association pour qu'on encourage tous celles qui ont l'idée de faire des mathématiques, pour qu'on ait plus de femmes mathématiciennes au Cameroun. Parce que si une voit déjà une comme moi, ça peut la motiver à faire les mathématiques. Elle dit que si celle-là a pu faire, pourquoi pas moi? C'est venu à part 2015. Quand je suis allée au Kenya, il y avait la rencontre des femmes mathématiciennes africaines. Quand je suis rentrée, j'ai dit il faut que je m'inscrive cette association. C'est pour ça qu'en 2016, la CAO m'a vu le jour. Bon, là maintenant, on peut avoir une vingtaine de membres. Et l'idée que j'aimerais faire de l'association, c'est qu'on la transforme un peu comme un laboratoire. Et chacune a sa spécialité. Moi, je suis en cryptographie, il y a d'autres qui font dans l'épidémiologie et ainsi de suite. Et là, maintenant, dans ces différents domaines, on va faire des connexions et ça va étendre notre association. C'est même l'un des objectifs de notre association, c'est de promouvoir les jeunes filles, les encourager à faire des mathématiques. C'est pour exemple pour laquelle nous commençons à partir du secondaire, on va chercher les enfants au lycée, on leur montre les bienfaits des mathématiques, on encourage à ce que quand elles ont le bac, elles vont choisir les mathématiques d'abord comme filière. Et quand elles sont à l'université, on les encourage à avoir une licence, on les motive à avoir un master, après on leur dit pourquoi pas un doctorat. On est à la fois maman, travailleuse et chercheuse, c'est pas évident de concilier tout ça. Et parfois, à un moment donné, tu as envie de laisser. Mon mari, c'est mon premier soutien parce que sans lui, je n'avais pas eu la thèse et même quand je suis à Marois, c'est lui qui s'occupe de ses enfants. Il travaille aussi. Il est enseignant. Il a aussi eu un doctorat en philosophie il y a 2 ans. Et oui, quand je suis à Marois, mes enfants me manquent beaucoup. Ils me manquent terriblement. Pour ne pas laisser, moi, ce qui me motive à ne pas laisser, je pense aux petites soeurs qui viennent, je les dis. Mon souhait pour le futur, c'est qu'il y ait plus de filles mathématiciennes. Parce que je me dis que la femme, c'est la mère de la société. Si vous la motivez, elle va faire mieux. Parce qu'une femme veut, elle peut, quand elle le veut d'abord. Et maintenant, quand elle le veut, il faut mettre les moyens pour l'aider à arriver là où elle veut arriver.
I come from a family with many strong women. My mother was an engineer, so I grew up always seeing her making computations. Iago loves nature. He likes playing with analytic toys, like toys that have some challenge, and I think I also encourage him to play with those, because they were also very part of my childhood. My partner is very supportive of my career. Sometimes have to travel by myself, and I feel safe that Iago is well taken care of by his father. My name is Carolina Araújo. I am a mathematician. I did my undergraduate in Brazil, and then I went to Princeton University to do my PhD. I thought that it was a very competitive environment, which I was not used to, and which did not really talk to my heart. I think that my best memories were in my last year of PhD, when we had a little group of women in mathematics. We used to meet for breakfast. Sometimes we would go biking in the woods together, and having that support was very important for me. I work at INPA, Institute for Pure and Applied Mathematics. I work with algebraic geometry. So I study geometric objects that are defined by algebraic equations. What I've been trying to do is to understand certain geometric spaces by looking at the behavior of curves on this space. My biggest achievement is to be a full researcher at INPA, and also I have been invited to be a speaker at the International Congress of Mathematicians in 2018. In Brazil, 25% of researchers in mathematics are women, but they're much less visible. It's not uncommon to see a conference where all the organizers are men and female speakers are sometimes even less than 10%. At this moment, I am the only female permanent researcher here at INPA. This low percentage, it's a problem everywhere in the world. We see this unbalance and this gender gap in mathematics. By excluding girls and women from mathematics, we're losing talents, brains that could be contributing to science. And I feel that it is my moral responsibility to help other women to also excel in their mathematical career. I have 2 female postdocs. They're talented women, and I think it's important to give them the opportunity to show their work and to excel in the career. Right now in Brazil, we are witnessing various movements of women in mathematics where we try to address the situation. So we organize roundtables and panels to bring this to the community. We're organizing the first world meeting for women in mathematics. It's a silent movement that's happening. This will certainly help in the long run to bring more women to mathematics. For the first time in my life, I am where I want to be. Not only I have achieved my scientific career, but also I am at the point where I feel that I can make a difference and I can contribute to the changes that we must make.
My work is in discrete geometry, having very little information and then being able to tell from that very little information what's the object you're ending up with. That's the sort of problems that I really like working with.
Lately, I am working with applications of algebraic geometry to the study of biochemical reaction networks, how the enzyme cascades, how the signaling pathway act in our cells, in our bodies.
Functional differential equations are very useful to describe some phenomena that do not occur instantaneously.
I work with probability that involves modeling of stochastic events, which means chance.
I work in reaction diffusion equations in mathematical models. You can give meaning to some important concepts in ecology through mathematics.
I work on pseudo-differential operators. I classify traces and determinants on algebras of these operators.
I think a lot of mathematicians talk about math like doing art, and I think that actually what we mean when we say that is that it's a passionate field, it's an exciting field, you have the freedom of thought. It's really fulfilling at a personal level and an intellectual level.
Once you get an answer, you get such a satisfaction. Gives you this impulse, this encouragement to continue and to do it another time.
In mathematics, you can really state something for a fact. Things make sense. I want to find theorems, I want to prove things. It's not just the laws of nature, but it's also the way how we make decisions. Sometimes we do some kind of mathematical reasoning even when we are not conscious of it.
Chance is everywhere. So many important things you cannot predict deterministically. I mean, they are subject to uncertainties, like the weather, like polls, understanding the social environment.
People say mathematics is not for me. This is not true. It's for you because you are human. We have the ability to speak and to do some math. There is a question of how mathematics could explain the world. We are inside the universe. This is why even if we put into words the circuits in our brain, I feel this is what we do when doing math. It's related to everything because we are constructed the same way as the universe.
What happens to women in mathematics is you are challenged constantly because somehow you're different and you do not fit in immediately with the image they have of the mathematician. You are in a gathering where everyone is male except you. It's not only about the codes, it's also about how a man believes that you fit in or not in this world. The most difficult part is like getting comments from professors where the implication was, you do not belong here.
When people look at me, they say, I don't think that you do mathematics. They don't believe me so easily, so I have to do more work in order for them to believe me. Usually, they ask me if I really did some work. They say, are you sure? Maybe someone else did it already, or it is wrong.
When I will give the first class for the students, they usually expect some old man that will come and give the classes. I never was discouraged to be a mathematician, especially because I had some strong women who inspired me a lot. Because of that, I have the strength to continue, and because also I like very much mathematics.
We are losing talents. We are losing points of view.
Mathematics has not been portrayed in a realistic way in the media, in school, everywhere. I think that we need to find a way to make mathematics more appealing, not just to girls, but to everybody, by showing mathematics how it really is. That it's a collaborative activity, that it has to do about thinking and not being fast, that it has to do about learning from others, about sharing experiences.
The world belongs to everyone, and being among the top mathematicians in the world with all the community makes you feel a part of something bigger.
I think the main way to motivate and to help is by your example. We just work. Now, people are starting to recognize the work of female mathematicians, and it is the work of many of them in all the areas of mathematics. Women are very talented, and you have to have the confidence that you know what you are going to talk about. And once you have this confidence, it's easier, because you know it, you just have to explain it.
Mathematics has this beauty of expressing many different phenomena to group them together in one beautiful concept. When women participate in science, the society wins because we can give something as women. We can give a perspective as women. So I think that when women get involved and when minorities get involved in any field, we all win. I think science wins.
We all have a very different experience of what's being a human being and being alive. And so having more inclusive mathematics ultimately is going to make more inclusive academia and more wholesome. And I'm sure that even though mathematics is super abstract, you bring everything in your culture with you to the table. And I think the science we will do is going to be a better science, and it's going to be much better implications for the world.
Welcome back, everyone. Professor Sylvie, are you here? Can we check some connectivity?
Hello. Hello to everybody.
Now we can hear you. How are you, Professor?
Fine. Can you hear me? Can you hear me?
Yes, yes.
Good.
We can hear you.
Good. Hello,
Really well.
everybody. So maybe I should share.
Yes,
share.
sure. We can check.
So, do you see my screen?
Yes, Professor, we can see your screen.
Good. So whenever you want to, I can start.
Okay, okay. Thank you very much, Professor. So after this beautiful video from Imu, it is my distinct pleasure to introduce Professor Sylvie Pecha, a distinguished mathematician and an inspiring advocate for equity and diversity in mathematics. Today, Professor Pecha will share with us her remarkable project, Women of Mathematics from Around the World, a gallery of portraits. This project celebrates the lives and contributions of women in mathematics, offering a unique perspective on their journeys and achievements. We are honored to have her with us today for this special session. Please join me in giving a warm welcome to Professor Sylvie Pecha. Thank you very much again.
Thank you very much. Thank you to you, Andrea. Thank you to Duvan and to all the other organizers I don't know, maybe directly or maybe I know without realizing I know them. So it's a real honor for me to talk on this occasion. And I'm sorry I couldn't attend any other talk because I'm myself organizing a conference in those 3 days. And I've just arrived from my workplace, Potsdam, to be able to be online here at my home for this talk. So thank you
very much again.
So I would first like to say there's another person involved in this project who is Noelle Matoff. I'll introduce her shortly in this talk. So there are 2 of us involved. And I'll go through a bit of the story of this exhibition, touring exhibition. And if there's time, you can ask me questions afterwards or during the talk. Maybe it'll be a bit difficult during the talk because I can't see who is asking a question. So it's a long story now because it's more or less 10 years old. And so in 10 years, lots of things happen. And it started as a modest project. And it started in 2014. And it was originally a project about women of mathematics throughout Europe. And now you saw that it involves women from all around the world. It's now got 34 portraits. Initially, it had 13. This is Noelle Matoff, who is a photographer, but also who helps me curate this exhibition. Among other things, she updates the webpage of the exhibition, which I think is a very useful networking tool. So it was her idea. She had nothing to do with maths. Now she has after 10 years. She had nothing to do with maths and liked the number 13. She thought it sounded very mathematical. So that's why we started with 13 people. And you see their names, and I'll talk more about the choice. So it's various generations, various topics of research, various geographic locations, and also various levels of recognition. Some of these women, you might have heard their names. Some of them, you might never have heard of them. And that's the idea. So that everyone can relate to one of them at least. Because it's easier to relate to someone who is not so famous when you're just starting yourself in the career of mathematics. So there's the date, 2016. And from 2016 to 2021, there were 13 portraits. And here are the portrait people. So There are some people like Oksana, like Kaisa, a few more, Irina, I think Alice too, whom we invited to this project because they were ex-Humboldt fellows. And we got funding from the Humboldt Foundation, thanks to whom we could start off the project. Before it even existed, the exhibition, they granted us with a prize. This prize was a 25,000 euro prize for networking. I thought it was quite something for them to grant us with a prize when the project wasn't even born. And also, it was an exhibition project. We didn't know that it would become, but it has indeed become a networking project. So we are very grateful to their support. And one of the conditions was to have people, ex-Humboldt fellows in the project. And that's how we got to know some of them I wouldn't have met probably otherwise. So this is in 2016, the opening at the Technical University of Berlin. I live very near, I am just now very near this university. And let me also tell a story, because I think those stories are interesting. We needed a place to present the exhibition. And once the German maths community understood that we were not going to select only using an excellence criterion, but having a diverse group of mathematicians, they stopped answering my emails when they had promised a substantial support. But since they saw that it was a mix of very famous and not so famous mathematicians, they stopped funding, and also we found nobody to host the exhibition until the librarian of the maths library at TU, at the Technical University of Berlin, opened his doors to us, not knowing us more than that, but he made it very nice. We had a concert with contemporary music by a composer, female composer, who we interviewed as well. So it was a very nice opening, thanks to him. So this was the 7th European Congress of Mathematics. Now, since then, it has traveled to more than 175 venues around the world. And Noel, the photographer, counted recently, so I think this is reliable. I just give you a few venues, which I'll comment along the way. But you see they're in alphabetical order, and since then I think there are a few more names among this list. Barcelona, Beirut, Bogota, Turkey, Diyarbakir, Gothenburg in Sweden, and Havana in Cuba. So just so that you see that the exhibition can be shown in various disguises. So we have a PDF file, which we send to whoever wants to print it out. For free, we send it. Then it's the responsibility of the local organizers to print it out as they wish. And here is an exhibition in Barcelona, in a very impressive hall of Barcelona. And here is an exhibition at the Universidad Nacional in Bogota, in Colombia. There we have the pleasure to be able to put them in frames, which we found thanks to the local organizers, one of whom I saw in one film just now that was shown online. in this event, Carolina Neira, who helped organize this exhibition locally. But we improvised everything. We had these posters printed out with the help of local people who funded the printing, etc. In Lebanon, Beirut, Lebanon, this was an exhibition, a portable exhibition that I could carry with me on the plane, rolled up, because there were 13 portraits at the time. But you see, 13 is quite a lot anyway. And this was thanks to a maths colleague of mine in Beirut, Georges Habib, who was not so interested in, supporting women, although he understands that he sees that there are not many women in maths, but it was not his first concern, but he was helpful enough to go out with me in the morning and find some pins to put them on some of these boards that we found in the corridor. And I like this photograph for the contrast between the veiled ladies looking at the panels. This is in Göteborg. So in some places, we have the support of men. There are a few men around the world who have supported us in a substantial way. And there's one in Göteborg who was, and I think is still, very supportive. This was in Havana, Cuba. And this, it's a very beautiful university for those who know the University of Havana, very similar in style to the one in Barcelona, I thought. And we had the pleasure to be able to use the balcony, a beautiful arched way balcony. And it was quite something finding this rope in Havana, where there were not in 2017, I think it's still now, even worse now, not many utilities available, but someone found this rope and we hung the portable exhibition. It's the same one as here. So you see it's got little holes there. We hung it on that balcony. And this is Turkey. There we weren't even informed of this exhibition in Turkey. We were informed after it had happened. This can happen because the PDF file, once we send it to someone, might travel along and then somehow it gets in the hands of some local organizers who take this initiative. So there are many other places where we showed this exhibition, and let me comment on two more. So this is in Senegal, in Bour. I was then invited to give some lectures in a differential geometry school, let's say. And this is the same portable exhibition, but that time I thought I wouldn't carry it. I would have it sent in advance. And we did send it long time in advance, but unfortunately it arrived after I'd left. I had to leave for teaching purposes in Germany where I work. And so I asked the people who were staying, I had to leave before the end, whether they could put it up, and they did. But before I left, I organized a discussion to prepare the local people to this exhibition, because it needs to be accompanied, to be explained, discussed. Otherwise, I think it becomes more lively if you talk about related topics when you present this exhibition. So I organized a small debate about women in maths in So this was in Senegal, and I think I organized it around Western African countries. There were indeed participants were maybe PhD students, master students, maybe a couple of postdocs from Western Africa, maybe South Africa as well, but mostly Western Africa. And mostly men, very few women. And they seemed very young, the few women who were there, maybe 3 women and maybe 25 men or something of the sort. And so I talked to the few women beforehand, asking them if they would be ready to say a few words. And they were all very shy and said, no, I can't talk. And I said, okay, well, we'll see, we'll just improvise. And that's what we did. And when the men, I think it was a group of men from the Ivory Coast who boasted, saying they had several wives, and their wives were not expected to have the same diplomas as they had. They should be less educated than they themselves. That would be a normal thing. They wouldn't like to have a wife educated better than they were. And they were going on and on like that until the 3 young ladies jumped up from their chairs and said, no, that can't be, and started defending their rights. And we couldn't stop them. They were so angry that they had forgotten about all their shyness and were frantically trying to convince these old-fashioned men, young men, that they had the right to have a higher education, just as these men had. This was in Quito, in an algebra South American Congreso Latinoamericano de Álgebra or something of the sort. And I think it was coming back from Colombia. It was the same portable exhibition in this hall. You see, it looks very different according to where you present it. It was also shown in schools, high schools, not that many, but now maybe 10. There's a list on the website you can see of the schools where it was shown. One of them was in the north of Paris. So you might have followed the Olympic Games and know that the Olympic Games took place in Saint-Denis, outskirts in the north of Paris. It's the poorest area, let's say département it's called, district in France. And that's where they organized the Olympic Games. There are some very fancy offices and now very fancy sports equipments, but most of the population has emigrated to France and lives in very modest or poor conditions. This school, which is called Iqbal Masih School, is one of the schools in that area, in this suburb of Paris, Saint-Denis, where a theater group, surprisingly, whose leader, whose director, is the son of a now passed away mathematician. So he's very sensitive to mathematics, and he had this idea of bringing his theater group into schools. And this theater group there chose to present the exhibition and to talk about women in mathematics. So they asked us whether the pupils could ask the women we had interviewed some questions. And so I said, of course, they could. They just would have to write these questions, send them to me, and then I would pass them on once they had been translated to English and formulated in a way that I think the portrait mathematicians could answer them. So they did. Some of the questions were very funny, like, do you have time to eat, or do you do mathematics all day, or do you dream of maths, or things like that. The English was hesitant, but anyway, a dialogue was set up between some of the portrait women. This is Katrin Wendland, this is Nalini Antanaraman, and others who answered their questions. And they deduce that's their point of view here. So that's their own panel they made, and their point of view is that it's not easy for women in mathematics, still not easy. So 5 years later, we were represented, this exhibition was represented at the 8th ICM. Remember, it was opened at the 7th ICM, and this at the 8th ICM in Portoros. Unfortunately, online, due to the pandemic, and thanks to these very active young women who made it possible to present the exhibition online. Neja here, you see, was later portrayed in the exhibition. And that's, so you see her again. So according to the funding we got, we tried to extend the exhibition when we got funding. I'll comment about how one extends the exhibition. And we decided to extend to the east of Europe and to the south of Europe. So east, you see, so this is Slovenia, this is Turkey, this is Kosovo, and this is Croatia and Greece and Spain. Now, Ragni is from the north, from Norway, so that came from a request from the Norwegian women in maths who wrote to us saying, we don't agree that Ragni Piene, our very famous mathematician, is not in the exhibition. So I know Ragni quite well, but we answered we can't put everybody in the exhibition, and although we know how important it would be for us to have her in the exhibition, but in the end we did, because Norway hadn't been represented. But of course, one can argue that the women in the exhibition are kind of, they're not randomly chosen, but of course it's one in representing one country, and it could be another one. There's a subjective choice, and also it's the fruit of encounters, of practical issues. It's not something we completely control. But the idea that the subject and subjectivity plays a role in this exhibition is fundamental, at least to me. Mathematics is supposed to be an objective subject where you don't put yourself as a subject forward, but you serve the subject mathematics in a neutral way. But as a woman, we can't be neutral because we're so underrepresented that we're obviously there as a subject. And I wanted to kind of stress this and put these women forward as subjects with their mathematics. So you always see mathematics accompanying them, or they accompanying their mathematics. Maybe I'll comment more about that. So we had a first catalogue with 13 portraits, then that's the 13, and then a second one, and you can see the countries here, which is, so I think this is, oh yeah, maybe I made a mistake, Montenegro. So these 7 countries, you see this is more Western, Northern, except for Dušanka from Serbia, Kasia, but Kasia is mostly in England. Oksana is now in Germany permanently. Irina, we met her in Germany. Alice is still in Hungary. and Stivka is still in Bulgaria. But there were, I think, Western Europe was overrepresented there. And it's a very nice catalog. I think I recommend that you, that's the only thing we sell because it's costly. Making it is costly. I'll comment on what it means to make these portraits and the catalog. So what's in the catalog are the full interviews we make with each of the portrait persons and photographs of the making of the interview while they are interviewed or while they're explaining their maths. Noel takes photographs. These photographs are in the catalog. So how does a session go? We've got a kind of ritual. I first, so how does it go? Yes. So we first ask the person we're going to portray to explain to me her maths. Usually her maths have nothing to do with mine. And so I ask her for half an hour to make her maths understandable to me. And we start a real discussion where I really try to understand and she really tries to explain to me. And while doing that, the person usually relaxes because she's then fully busy with the explanations and she forgets the photographer, Noel Matov, who's standing there taking photographs. And many of these photographs where I appear, so here you don't see them, but in the catalog you see them, are taken while the person is explaining her maths to me. I get involved, she gets involved, and we forget the camera. Then Noel asks me to disappear for a moment, and she takes a photograph. These are those photographs here of the person in front of the result of her explanations on the board. We ask her if she's happy with what's on the board. Sometimes she changes something because she thinks it might be a mistake. Usually she's happy. And so it's a board she should be proud of. And that's the photograph with a old-fashioned camera. Noel takes this photograph. Then after that, Noel retrieves and I do an interview. I interview the mathematician for about an hour. So there are a few set questions, but we digress rather fast. I try to keep on track to have a common thread, but the exchange the dialogue can be very free. So that's the list of women, and but now you see new ones, so from different countries which are non-European. So that was extending beyond Europe. So Tunisia, that is, there are a few. So there are two from Tunisia. Here, there's one, and one who is French, Claire Voisin, but whom I interviewed in Tunisia. This is thanks to the president, the then president of the Tunisian Math Society, a man who kindly funded the portraits for these three women. So you see, the photographer, Noel Matov, is freelance. So unlike me, she doesn't have a regular salary. And when she takes these photographs, it's time and energy and work taken from her usual work. So she needs to be paid for that. Then the catalog needs a graphic designer, needs to be printed, etc. So the costs are quite high. And that's why we need every time some funding. And the portraits, the panels also have to be designed by a graphic designer and then put in shape. And all that has a cost, and quite a substantial cost. And that's why the catalog is not free of charge. So we first tried, wait a minute, let me get that right. There was going to be a meeting, Women in Mathematics. I see there's a mistake here. In 2022 in Japan, organized, I think, by Yukari Ito then, who is in Tokyo at this research institute, Kavli IPMU. And but she had to cancel it, or I think we did it partly online because of the pandemic, which was still, there was still strict regulations in Japan. But then, so we nevertheless managed, Noel and I, to go to Japan, invited by Yukari, and then invited by Reiko at the OIST Institute, which is an interesting spaceship-like looking institute in the island of Okinawa, where we organized together, but Reiko did most of the work for that one, a meeting called Women at the Intersection of Mathematics and Theoretical Physics, Meet in Okinawa. So this, I'll explain a little bit. I work at the intersection of maths and theoretical physics. Although I'm a mathematician, I borrow ideas from physics. And maybe some of you know, there are even fewer women in those areas. And we felt the need, maybe 10 years ago now, I don't remember when we started, with, in particular with Kasia Reisner, who you saw in one of the portraits, from Poland originally, working in York in England. We felt the need to organize meetings for women at the intersection of maths and theoretical physics. And we have organized now 6 around the world. Let me think: Mainz, Hamburg, then Geneva, then so Canada, and then Japan, and now we're trying in India. So it will be the 6th. This is Kasia here. And this is not so old. You see, it's 2023. So I've been organizing for many decades, but now it's come to an end. Summer schools in Villa de Leyva, a beautiful colonial town in Colombia, which are also at the intersection of maths and physics. And they used to be 3 weeks long, then they shrunk to 2 weeks, and now they've disappeared more or less. And this was the last one in 2023. And this is the patio of a very nice hotel. And it was very funny. We're smiling because it took us ages to figure out. So I had them printed out here in a tiny scale due to, I mean, it was really improvised. So we didn't have many means. I just went to the local shop and saw what could be done. We could print them out like this. And so we had to try to deal with the winds, which would blow them up. And it took ages to find a system by which they would, stay straight, and we could watch them. And there were physicists and mathematicians incapable of finding an immediate solution. Then I went with this exhibition, in my case, to Ghent. So Duvan is here, and I think you were there when we did that. And there too, it's always sometimes very funny watching men. Usually it's men, because mostly they're men in those meetings, putting up portraits of women. Usually the portraits are much bigger. And so you see these men carrying huge portraits of women around the room. It's quite funny sometimes. So recently, so this is last March, So I've been working with two colleagues for decades at Sichuan University, Chengdu. I've got a colleague working there, and he knows that for me, women in maths is a subject. He's getting now interested, and he kindly enabled us to show the exhibition there. I didn't bring it with me. I just asked him to print it out. And we went to the local printing shop of the campus in Chengdu, Sichuan University, which is tiny, really tiny, and it doesn't look like a real shop, full of paper, full of printing machines. And I never thought they would spit out a whole exhibition, but the next day they had these beautiful portraits ready for us to put up. Cornélie is a young mathematician I met in Ouagadougou, in Burkina Faso, when I organized a school there. I was going to say summer, but a very singular school, and it was on singular geometry or analysis. It was on Fourier integral operators. It was very singular because there was a coup. Diendéré ruled out the then president of Burkina Faso. So we were stuck. We couldn't fly back. It was a very unique experience. Anyway, Cornélie, who comes from Congo, was there. And I've kept in touch with her since then. We sometimes, she tells me what she's done, and she did brilliantly. Was, I think, the youngest PhD student who got their PhD in her country, I think, something quite incredible. And I had the surprise to hear that she would be in Japan for some time, for a year, as a postdoc, which I find very brave for someone from Africa, because in Japan, it's not easy for women in science, and it's not easy as a Black person. But, and I invited her to this meeting we had in Okinawa, and so we were able to make her portrait. Motoko Kotani is a very famous mathematician in Japan who has huge responsibilities. She's the head of a big institute, interdisciplinary research institute in the north of Japan. And I had the pleasure to interview her when she was in Tokyo. And it was a very nice interview. And then when I interview, then I write up the interview and I send it to the people to make sure that they agree with what's written. Do they would like to change something, to complement? And one of the questions is, did you meet any obstacle in your career? And she told me very, ordinary obstacles people talk about, or maybe features of a female career, that she was on many committees, like most of us, many committees, because they need women on committees, and that because of that, she got acquainted with administration and heading committees, etc. And she went up in the scales and reached these very interesting positions that she's now holding. And I thought it was a very neutral reply, and I was surprised when I sent her the interview to her answer was, please take out the reply to what I said about the obstacles. And I insisted a bit, saying, if it looks as though you've never come across any obstacle, probably most women won't relate to you, because most women go through some difficult phases. She said she could very well understand, but I had to understand that for her, as a woman in Japan, it was too risky to formulate any criticism towards her male colleagues. So I took out this part on the obstacles, and it's the only interview where I had to take it out. I had to take out anything among the 30, or I don't know how many I've done, 50 maybe. So 8 years later, this is very recent. This was in last summer. It was in Sevilla, south of Spain, the ECM, and thanks to Diana McLagan in Warwick, we organized a roundtable and presented the exhibition thanks to the organizers of this ECM, who I think Isabel Fernandez is one of them, who amazing organizers who were very open and very responsive when we asked them whether we could show the exhibition. So this is the initial funding, Alexander von Humboldt, TU Berlin for the library that hosted us. Then we got some money from the Robert Bosch. This is unfortunately military oriented, but not only. This is an artists organization which helped Noël at least a bit financially. This is my university, which helped a bit. And this is EWM, which helped for some of the travel expenses. Now, the exhibition has sister exhibitions in the world, and one of them is thanks to Mariel Saez from Chile, who once wrote to us asking if she could do some interviews and portraits similar in spirit to the ones we had done. And I see that Alicia Dickenstein was mentioned in the film we just saw, Carolina Neira Jimenez as well, probably, maybe others here. Anyway, so she interviewed these women from around South America. Of course, it's only 11, but and the catalog, accompanying catalog in Spanish is very nice. I recommend. Carolina again, Neira in Colombia, together with, I think maybe Eddie is the initiator in the Universidad Pontificia Javeriana in Bogota. They organized this exhibition also touring exhibition in Colombia, where they had women and mathematicians from remote regions of Colombia interviewed and portraits. You find this exhibition online, and I find a common feature is their beautiful smile. They all smile with a beautiful smile. This is Pierre Portal, French, who's at the ANU in Canberra, capital of Australia, one of the biggest universities in Australia. And I didn't know him, but he contacted me some years ago, forgotten, maybe 2018, 17, asking me if I could come for a visit to talk about maths and also about women. So we did both. And when we started talking about women, then I think I brought the exhibition. I don't remember exactly how it came up, but came up the idea of interviewing women in Australia. Now, the problem was, how would we do it for the photographs? Because Australia is not too near. And I've often heard when I go anywhere, if my travel expenses are covered, it's because I give a maths talk. And so in Bonn at the Max Planck Institute, where we presented the exhibition a long time ago, they told us that they could cover expenses for formulae, but not for photographs. And that's what often happens when I go anywhere with this exhibition. I give maths talks, and this way I get my travel expenses covered, but Noël Matoff cannot give a maths talk, so it's a real problem. So she couldn't come, and we had another photographer, who did the photographs. So I didn't really choose the list of women, apart for a couple, let me see if I find her. There's Rowena Ball. Oh, she's not here. You don't see her here. She's from Aboriginal origin at the ANU, professor there. And when I asked, I had kind of met her in the corridor and vaguely talked to her. And when I asked whether I could interview her, they said, "Oh, I don't think she'll say yes, you know." And in fact, she did say yes, and she was very open. It's a very interesting interview, fascinating person. And there are young people, as you see, I interviewed from different origins. And there are very sad stories I heard, and very sad stories that happened after this. Some of you might recognize names which have unfortunately become famous due to scandals, but from which these women suffered. So I felt there was a beginning of a Me Too, which I wouldn't be surprised could maybe explode anytime in maths. Women who suffered from their supervisors who were ill-treated or disrespected or even more. So this is all for now. Let me thank you for your attention, and I'm open to questions.
Thank you very much, Professor Sylvie, for this nice presentation. I encourage everyone here to explore Professor Sylvie's project and catalog. It is really nice. It is really well done, everything. And reflect on how we can all contribute to greater diversity and equity in our communities. Someone wants to ask something or say something.
Maybe I can ask something to Professor Sylvie Pacha. Of course, first of all, just let me say thanks for presenting this for doing this very inspiring presentation. My question is the following: in your opinion, what has been the more valuable, let's say, experience being the leader of this project?
First of all, there are two people involved with
okay.
Noel. I wouldn't call myself a leader. I think it's having the privilege. So I think it's quite amazing. I don't know these women. And when I interview them, we find ourselves in a room, often not a familiar room to them, nor to me. And they start telling me about their lives. And it's quite amazing to be able to share their experiences, and sometimes very personal and some of them traumatic experiences. So that I find amazing, that, you know, in 1 hour, somehow we get this intense communication.
Okay. And maybe second question, Professor Pacha. This year, Karina Navarro and Andrea Hurtado, she started this series of conferences, right? With the support of ICMAM Latin America and ISAAC, right? So my question or comment is, which advice you can provide to them, maybe to continue with this kind of initiatives that are very
difficult question. I think I don't know enough about the project to say. what I would say spontaneously, but I don't know enough about the project, is to make sure that you don't attract only well-known people, and that one looks for women in the corners of mathematics whom we might have left aside. I think that's important because there are lots of valuable work being done by women who don't stand in the forefront, and because they haven't had the chance or whatever. And so that takes time because you don't reach them so easily. But maybe that could be one general advice, but I don't know enough about the project to give pertinent advice.
Thank you very much, Professor, for this advice. You're a referent and a mentor. Thank you very much for accepting this invitation again. You must be really tired because thank you for accommodating your schedule. You also have this conference aside. So thank you very much to find the time to just give us your time.
Well, thank you for hosting me. Thank you for listening at this time of the day for some of you, and hope to keep in touch and hope to be able to attend some of your talks and meetings. Thank you.
Sure, Professor. Thank you very much.
Thank you so much.
Adiós.
Bye. Adiós.
Adiós.